33 trillion kilograms. That's the minimum mass now assigned to our latest interstellar visitor known as 3I Atlas. To grasp just how colossal this object is, consider that it surpasses the weight of the Empire State Building by a staggering factor of 40,000. Yet remarkably, this cosmic heavyweight drifts effortlessly through the vast emptiness of space, emitting active jets of gas while showing almost no sign of orbital disturbance caused by its own outgassing. It's as if we're watching a freight train powered by nothing more than birthday candles. An image that underscores the sheer paradox of this object's behavior. But what makes this discovery even more perplexing is that, given its immense size, we would have expected to find dozens of smaller objects, smaller fragments and debris, long before encountering such a massive entity. And yet, we didn't. This discrepancy suggests that either our understanding of how cosmic debris populates interstellar space is fundamentally flawed, or we are witnessing something entirely unexpected, phenomena that challenge the very nature of what exists between the stars. It's a moment that beckons us to reconsider established theories about the distribution and behavior of interstellar objects. Tonight we delve into the groundbreaking findings that may be rewriting the rules of interstellar archaeology. These revelations prompt us to confront a disconcerting question. What else are we missing in our exploration of the cosmos? The discovery of 3I Atlas isn't just an addition to our catalog of interstellar visitors. It's a potential paradigm shift, one that urges us to reevaluate the very assumptions that underpin our understanding of the galactic debris field. Odin, the shockwave announcement. Recent analyses have produced astonishing estimates. 3I Atlas weighs at least 33 billion tons with a nucleus that's at least 5 kilometers across, orders of magnitude larger than any previously observed interstellar object. If these figures hold true, our entire picture of interstellar debris has just been shattered. The numbers originate from Harvard's Center for Astrophysics, where scientists meticulously analyzed more than 4,022 positional measurements obtained from 227 observatories spread across the globe. This isn't mere speculation. These measurements establish a firm lower limit, though they remain preliminary. The implications are staggering. Let's take a step back from the complex math for a moment. What's particularly striking is that astronomers detected virtually no measurable non-gravitational acceleration, no significant push beyond what gravity would induce. When considering outgassing, the process where ice sublimates into gas as a comet warms, the limit sits below 15 meters per day squared, or about 2 times 10 to the negative 9th meters per second squared. When converted into familiar units, we're talking about forces so minuscule that they barely register above the background measurement noise. Here's where the puzzle deepens. In physics, the rocket effect, the recoil generated by active outgassing, is well understood. As a comet's ice sublimates, the escaping gas produces jets that gently nudge the object, nudges that accumulate over time and alter its trajectory. We've observed this phenomenon countless times in the solar system. Typically, when a comet warms near the sun, outgassing of water vapor, carbon dioxide, and sometimes more exotic compounds creates a measurable orbital push. But in the case of 3I Atlas, despite clear signs of active outgassing, the expected orbital acceleration isn't there. The object is clearly shedding material, water vapor, carbon dioxide, and other compounds, yet it behaves as if it's almost immune to the recoil effects that should accompany such activity. The only plausible explanation? It must be incredibly massive. A huge mass absorbing the recoil without noticeable change in its orbit. Why does this matter? Because it reflects a fundamental challenge to our current understanding. A previous interstellar object, Oumuamua, exhibited anomalous acceleration that puzzled scientists for years. Two other objects, Borisov and Borisov-like, behaved like typical small comets, reassuringly familiar. But 3I Atlas is different. It appears to be an active, gaseous body, a true heavyweight. Yet it shrugs off its own breath as if it were a mountain ignoring the morning mist. We're entering a regime of physics we've never encountered before. The reaction within the scientific community has been nothing short of fascinating. Curiosity is mingling with skepticism. The initial reports and analyses are summarized accurately, emphasizing that these findings have not yet undergone peer review. This is how science should progress. Extraordinary claims are scrutinized through the rigorous methodical process of peer evaluation. The tension is palpable as everyone awaits further validation. Yet the implications of this discovery are already resonating deeply. The atmosphere around the discovery is tense, as the scientific community collectively holds its breath, pondering the implications of this extraordinary find. Let's clarify what we know with absolute certainty. This object marks only the third confirmed interstellar visitor ever observed in our solar system. A rare and precious glimpse beyond our familiar cosmic neighborhood. It was first identified on July 1st, 2025, by a dedicated observatory nestled in the clear skies of Chile. The Minor Planet Center officially assigned it the designation C2025N1, Atlas, a formal label grounded in its discovery date and trajectory. Yet in scientific circles and among enthusiasts alike, it is more commonly known as 3I Atlas, the 3I standing for Third Interstellar, a subtle reminder of just how uncommon these wandering cosmic travelers truly are. As the field of interstellar object detection pauses in anticipation, it's important to establish that Earth remains entirely safe from this visitor's path. Its closest approach to our planet will occur on the 19th of December, 2025, when it will pass at a distance of approximately 1.8 astronomical units, roughly 170 million miles away. To put that into perspective, this is closer than some of the asteroid flybys we've observed, yet still well beyond the range of any danger to our world. We are mere observers in this cosmic ballet, watching from afar, not targets for impact or collision. The visual evidence collected from multiple vantage points offers a compelling narrative of its nature. The Hubble Space Telescope, renowned for its detailed imaging, photographed 3I Atlas on July the 21st, revealing an unusual shape, what astronomers describe as a teardrop-shaped cocoon. Its structure is enveloped in an irregular glowing shell, with an intriguing feature, a bright sunward glow. This is notable because most comets, influenced by solar wind and radiation pressure, develop tails that always point away from the sun, pushed outward into space. Instead, Atlas exhibits an anti-tail, a luminous extension pointing toward our star. An uncommon phenomenon that raises eyebrows among experts and hints at complex activity beneath its surface. Further observations made by the Gemini South Telescope on August the 27th showed this anti-solar tail growing more prominent over time. The evolving shape suggests that the object's surface and internal properties are responding dynamically as it warms, approaching the sun. The morphology of the comet's dust and gas flows indicates intricate dust dynamics and gas flow patterns, painting a picture of active sublimation and complex internal processes. Each new image adds another piece to the puzzle, clues that will help determine its true mass and composition. Now, this is where the numbers become truly astonishing. If 3I Atlas truly possesses a nucleus about 5 kilometers across, a size comparable to a small city, and if its mass exceeds 33 billion tons, then it is 3 to 5 orders of magnitude more massive than the previous interstellar objects we've encountered, such as Oumuamua or Borisov. This is no modest upgrade. It's a leap from tiny pebbles to massive boulders, transforming our understanding of what kind of debris can drift through interstellar space. Based on population statistics and models of planetary system ejection, we would expect to discover smaller, more numerous objects first, those easier to eject, more common, and requiring less energy to accelerate to interstellar speeds. Yet here we are with 3 interstellar visitors passing through, and the latest is potentially the largest of all. It's akin to discovering elephants before you find mice, upending assumptions about the distribution of interstellar debris. The mass estimates hinge critically on assumptions about outflow rates, the amount of gas sublimating from the surface, and gas velocities. The James Webb Space Telescope, which observed Atlas on August 6, 2025, provided pivotal spectroscopic data. Its infrared spectrograph detected signatures of water ice, water vapor, carbon dioxide, and carbon monoxide, offering insights into what is sublimating from the object's surface. These measurements are vital. They help connect what we see, the visible activity, with what we cannot directly observe, the invisible mass. However, the models translating these spectroscopic signals into mass estimates are only as accurate as their inputs. Currently, those inputs are still being refined as scientists work to improve their understanding of gas flow rates and velocities. The chemical composition revealed by JWST adds another intriguing layer to this puzzle. The ratios of volatile compounds, especially the high proportion of carbon dioxide relative to water, are among the highest ever observed in a comet at such a distance from the Sun. This suggests that Atlas may have formed far from its parent star, in a region known as the carbon dioxide snowline, where temperatures are low enough for carbon dioxide to freeze solid alongside water. Most comets that originate closer to the Sun show different volatile signatures, making Atlas's chemistry stand out as a clue to an exotic, perhaps interstellar formation environment. In essence, what we observe is a celestial object that defies straightforward classification. Its shape, its 3I Atlas, appears to be enriched with compounds that demand extremely low temperatures to condense, an indication that it likely formed in the cold, distant outer regions of a far-off stellar system. This chemical fingerprint essentially serves as a signature of alien ice, revealing clues about its icy origins in environments far removed from the warmth of a star. However, it's important to keep a balanced perspective. The figures that have led scientists to consider 3I Atlas as a silent, colossal entity are based on preliminary estimates of its outgassing rates, around 150 kilograms per second, and gas velocities near 440 meters per second. These values, however, are highly dependent on the models used and will undoubtedly be refined as further analyses are published and more data becomes available. The team behind the James Webb Space Telescope has yet to release their definitive measurements, so these estimates remain provisional. Nonetheless, the fundamental physics underpinning these findings are difficult to contest. If an object shows active gas production, visible through the formation of a coma or jets, yet produces no measurable recoil or rocket effect, then something about the situation must be reconsidered. The options are limited. Either the gas isn't escaping as efficiently as it appears, which seems unlikely given the clear evidence of a visible coma, or the object must be sufficiently massive to absorb the recoil momentum without noticeably changing its trajectory. Present evidence leans strongly toward the latter, meaning that 3I Atlas is likely an extraordinarily massive object. To visualize this, consider a fitting metaphor. Imagine someone trying to move a freight train by throwing tennis balls at it. The tennis balls bounce off, but the train remains immovable. Observers watching this scene would quickly realize they're dealing with something far more substantial than the appearance of a few bouncing balls suggests. In this case, 3I Atlas seems to be the freight train, an interstellar object of immense mass capable of shrugging off the sublimation-driven jets without any noticeable change in its course. This realization prompts troubling questions about our current understanding of the galactic debris field. If such massive objects are out there, objects capable of withstanding the recoil from outgassing, then where are all the smaller counterparts we expected to find first? Are these smaller fragments simply invisible to our current surveys? Could they be destroyed over time by interstellar erosion, or are they much rarer than our models predict? The implications reach beyond mere academic curiosity. The upcoming Vera Rubin Observatory, with its ability to scan the entire southern sky every few nights, promises to revolutionize this field. It could potentially discover dozens or even hundreds of interstellar objects each year, drastically expanding our data set. If 3I Atlas is representative of the typical size and mass of interstellar visitors, rather than a rare outlier, then our existing theories about planetary system formation and debris ejection may need significant revision. It suggests that the population of interstellar objects could be far more diverse and massive than previously thought. So what specific evidence has led researchers to hypothesize that 3I Atlas might be a silent, massive giant? And can we genuinely trust this hypothesis? The case for the silent giant is built on a compelling trilogy of evidence. First, there is an upper limit on its non-gravitational acceleration, so small that it is barely distinguishable from zero, indicating an almost complete absence of recoil from outgassing. Second, multiple observatories and space telescopes have captured visible signs of cometary activity, jets, comas, and sublimating gases. Third, the JWST has revealed an unusual chemical composition rich in carbon dioxide, setting this object apart from typical solar system comets observed at similar distances from the Sun. To understand the significance of the rocket effect, picture a garden sprinkler spinning as water streams from its nozzles. The escaping water exerts tiny forces that cause the sprinkler to rotate or change its trajectory gradually. Similarly, when a comet's ice sublimates, jets of water vapor and other gases produce small but measurable pushes that can alter its orbital path over time. This physics is well understood and has been observed in hundreds of comets, where non-gravitational accelerations, minute deviations from purely gravitational trajectories, are routine. Yet in the case of 3I Atlas, despite unmistakable signs of outgassing, water vapor streaming away at hundreds of meters per second, the expected orbital nudges are conspicuously absent. The observations reveal a vast, extended coma of carbon dioxide stretching across hundreds of thousands of kilometers from the nucleus, indicative of active sublimation. Yet despite this clear evidence of outgassing, the expected orbital influence, an orbital nudge caused by the recoil from escaping gases, is conspicuously absent. The limits of this acceleration are astonishingly low, measured to be below 15 meters per day squared, effectively indistinguishable from a purely gravitational trajectory. To put this into perspective, compare this to what we know about our first confirmed interstellar visitor, Oumuamua. That enigmatic object exhibited a measurable non-gravitational acceleration despite showing no signs of cometary activity or visible outgassing, an apparent contradiction that sparked widespread debate. Scientists proposed explanations such as hydrogen outgassing or the influence of solar radiation pressure acting on an unusually elongated shape, but the mystery persists to this day. In contrast, the interstellar object designated Borisov, discovered in 2019, provided a reassuringly familiar example. Its behavior aligned precisely with what we observe in typical solar system comets. Spectroscopic analyses revealed the presence of water vapor and carbon monoxide emissions, spectral signatures of well-understood cometary volatiles. Its nucleus measured roughly 1 kilometer across, and the non-gravitational acceleration it experienced matched expectations based solely on physical outgassing physics. Borisov's predictable behavior reassured scientists that interstellar comets could mimic the activity and dynamics of their solar system counterparts, reinforcing the idea that such objects are natural and familiar in their physics. However, the third interstellar visitor, known as 3 Atlas, challenges this conventional understanding. It occupies a vastly different region of parameter space. The comet's activity, manifested through visible outgassing and volatile emissions, suggests a typical cometary process. Yet the physics that should govern this activity appears to be fundamentally at odds with the observed orbital motion. It's akin to watching someone swim through water without getting wet, a scenario that defies basic physical principles unless some fundamental assumptions are incorrect. The chemistry of 3 Atlas adds an extra layer of intrigue. Observations from the James Webb Space Telescope's near-infrared spectrograph on August 6th detected not only the usual suspects like water ice and vapor, but also significant amounts of carbon dioxide and carbon monoxide in unusual proportions. Remarkably, the ratio of carbon dioxide to water is among the highest ever measured in a comet at this heliocentric distance. This particular chemical signature strongly suggests that 3 Atlas formed in the extreme outer regions of its parent system, beyond what astronomers call the carbon dioxide snow line, an area where temperatures plummet below -125 degrees Celsius. Most solar system comets are believed to have originated closer to their parent stars, where water ice tends to dominate over carbon dioxide ice. The fact that 3 Atlas carries the frozen remnants of such an unusual cold environment implies it was born in conditions that are truly alien compared to typical solar system comets. Supporting this, the space-based infrared telescope SphereX detected an expansive carbon dioxide coma extending hundreds of thousands of kilometers from the nucleus. This signifies a more gas-rich and voluminous envelope than casual telescopic observations might reveal, an enormous invisible atmosphere surrounding the solid core. While visible light images show a relatively compact, bright nucleus, the infrared observations expose a vastly larger and more diffuse gaseous shell, highlighting the complex and unexpected nature of this object's activity. Now here's where the physics become particularly troubling. Even modest outflow rates of gas, on the order of hundreds of meters per second, should produce a recoil force on the nucleus, transferring momentum and causing measurable acceleration. According to the law of conservation of momentum, the escaping gases should impart a detectable push to the parent body. For a nucleus about 1 kilometer in diameter experiencing typical gas loss rates, this recoil should be easily measurable through precise astrometric observations. Yet an extensive data set comprising 4,022 positional measurements from 227 observatories collected over a span from May 15th to September 23rd of 2025 shows residuals that are consistent with a purely gravitational trajectory. No detectable non-gravitational acceleration. This presents a profound physical paradox. On the one hand, the evidence indicates robust outgassing and volatile activity, and on the other, the object's orbit shows no signs of the recoil effects that such activity should produce. The observations, meticulously gathered over more than 4 months, pose a challenge to our fundamental understanding of comet physics and the relationship between volatile activity and orbital dynamics. Over a span of more than 4 months, scientists meticulously gathered data as cometary activity steadily intensified as 3I Atlas journeyed closer to the heart of our solar system. This period of observation was critical, capturing the transition from quiet intrigue to active phenomena, and the calculations involved are surprisingly straightforward yet profoundly revealing. By understanding 2 key parameters, the rate at which gas is produced and the velocity at which that gas escapes, we can determine the expected recoil acceleration that the object should experience due to outgassing. If, upon measurement, the actual acceleration, that subtle push imparted by the escaping gases, is significantly less than this calculated expectation, it suggests a startling conclusion. The object must be far more massive than initial estimates indicated. This process resembles detective work, with the principle of momentum conservation acting as the primary witness. It's a puzzle where the physics provides the clues. Currently, estimates posit that 3I Atlas loses approximately 150 kilograms of mass every second through active gaseous outflows. To the casual observer, this might seem modest, roughly equivalent to the combined weight of 2 people each second. However, when you extend that loss over days and weeks, the cumulative effect of momentum transfer becomes substantial. It should, in theory, gradually nudge the object into a measurable non-gravitational orbit change, an orbital nudge that exceeds the detection limits of our instruments. Yet the observations tell a different story. This expected push remains below the threshold of detection. The absence of such a measurable recoil implies that the object's mass must be extraordinarily large. Applying conventional assumptions about comet densities, around 500 kilograms per cubic meter, the lower boundary of the object's mass, estimated at approximately 33 billion tons, translates into a nucleus at least 5 kilometers across. Such a size is genuinely enormous within the context of interstellar visitors. To put this into perspective, the first interstellar object we ever observed, Oumuamua, was estimated to be less than 1 kilometer in its longest dimension and probably weighed only a few million tons. Similarly, Borisov's nucleus was roughly 1 kilometer in diameter and contained billions of tons of material. In comparison, 3I Atlas potentially surpasses both of these previous visitors by factors ranging from 10 to 1,000, marking it as a true heavyweight in a field that traditionally features much smaller objects. The velocity at which the gases escape, around 440 meters per second, comes from spectroscopic analysis of emission line profiles. When gases flow from a comet's nucleus, their thermal motion and bulk flow combine in characteristic ways that broaden spectral lines, allowing scientists to model and estimate the speed of these outflows. These velocity estimates are consistent with what we see in our solar system's comets. Sublimating water ice and other volatiles typically produce escape speeds in this range, influenced by the sublimation energy and the relatively weak gravity of small nuclei. What's truly perplexing, however, is the stark disconnect between the significant production of gas and the negligible orbital response. To clarify this paradox, consider a simple visualization. Imagine plotting the mass of a comet against its non-gravitational acceleration for all known objects. In our solar system, these objects tend to cluster along a predictable relationship. Larger mass corresponds to smaller acceleration at a given level of outgassing activity. Oumuamua, for example, was off to one side with a high acceleration but no visible signs of gas activity. Borisov, on the other hand, aligned well with the main trend, behaving like a typical comet. Now place 3I Atlas on this diagram and it occupies a bewildering no man's land. A combination of high mass with very low acceleration, defying the expectations set by known physics. It's as if we're looking at a massive object that, despite actively sublimating ice, somehow shrugs off the recoil. The analogy writes itself, like a vast silent boulder that looks and breathes like a comet but behaves as if it's impervious to its own outgassing, challenging our fundamental understanding of how these objects should work. The stark contrast between how the object appears and how it moves raises some uncomfortable questions about what exactly we are observing. Could our estimates of gas production be inaccurate? It's a possibility, but spectroscopic data from the James Webb Space Telescope provides strong and reliable constraints on the rates at which gas is flowing away from the object. Could the measurements of its acceleration be systematically biased? This seems unlikely, especially given the extensive network of observatories worldwide and the meticulous error analysis they perform. Could the fundamental physics of momentum conservation simply be suspended here? Certainly not. This leaves us with mass as the most plausible explanation. In essence, 3I Atlas seems to be a genuinely and remarkably massive object, a quiet giant hiding behind the appearance of an ordinary comet, until the precision of measurements uncovered its true nature. But who was able to gather data precise enough to detect such minuscule effects? This question leads us to the third part of our story. The Global Eye Network. The tale of 3I Atlas unfolds through the collective efforts of hundreds of telescopes distributed across the Earth's continents. When researchers Avi Loeb, Andrea Cloete, and Robert Very compiled their analysis, they drew upon a staggering 4,022 individual measurements contributed by 227 observatories, all collected between May 15th and September 23rd of the year 2025. This campaign represents one of the most comprehensive and detailed tracking efforts ever undertaken for an interstellar visitor. At the core of this effort is the precise measurement of celestial positions, a discipline known as astrometry, which forms the backbone of orbital mechanics. Every telescope that observed 3I Atlas recorded its position in terms of right ascension and declination, essentially celestial longitude and latitude. These measurements, accurate to fractions of an arcsecond, accumulated over time to produce a detailed map of the object's motion against the backdrop of the star field. Think of this process as cosmic detective work. Each positional measurement is like a single snapshot, a frame in a long exposure photograph capturing the object's orbital journey. When enough of these frames are linked together, patterns emerge. Any deviations from a purely gravitational trajectory become apparent as systematic residuals, the subtle differences between where the object actually appears and where gravitational physics alone would predict it should be. Detecting effects as small as those exhibited by 3I Atlas requires extraordinary precision. To put it into perspective, the positional shifts under scrutiny are smaller than 28 thousandths of an arcsecond, an almost unimaginably tiny angle. For comparison, that's akin to discerning the width of a human hair from a distance of 20 kilometers. Yet ground-based telescopes routinely reach this level of accuracy through careful calibration and the statistical analysis of multiple measurements. So how does this extraordinary positional accuracy translate into limits on the object's acceleration? The relationship relies on the principles of orbital mechanics and the geometry of the observations. Small accelerations over time cause the object's position to shift in a quadratic manner, meaning the displacement grows proportionally to 1/2 times the acceleration multiplied by the square of time. After months of diligent observation, even the tiniest non-gravitational forces should create orbital deviations that are detectable. From this analysis, an upper limit on the non-gravitational acceleration of about 15 meters per day squared emerges. Although these units sound unwieldy when converted to more familiar terms, they amount to roughly 2 billionths of a meter per second squared. A minuscule force, yet one that should be measurable with the precision of modern astronomy. The level of measurement precision required is truly staggering. So minute that it's approximately 110 millionth the acceleration experienced in a gently moving elevator. Achieving such exquisite accuracy demands a meticulous, almost detective-like approach, piecing together thousands of tiny positional clues to construct a trajectory precise enough to test the very fundamentals of physics. Every observatory involved plays a vital role, bringing its unique expertise and vantage point into this grand collaborative effort. During the summer months, observatories situated in the Northern Hemisphere diligently track the interstellar visitor, known as 3I Atlas, ensuring continuous monitoring as the Earth's rotation reveals new regions of the sky. As the seasons change, observatories in the Southern Hemisphere assume the crucial task, maintaining the global watch. The entire discovery process unfolds like a modern-day astronomical thriller, an intricate chase that exemplifies the speed and sophistication of current science. 3I Atlas was first spotted by Chilean astronomers on July 1, 2025, initially catalogued as a potential asteroid. But subsequent recovery images, archived photographs taken before the object's formal discovery, helped refine its orbital path and confirmed its interstellar origin. Within just a few weeks, the Minor Planet Center officially reclassified it as humanity's third confirmed interstellar visitor, marking a milestone in our exploration of objects traversing interstellar space. Meanwhile, the Vera Rubin Observatory, still in its commissioning phase, contributed early imaging data. These observations were instrumental in assessing the object's activity levels and establishing precise astrometric measurements, exact positions against background stars, setting the stage for a new era of astronomical surveys. This emerging landscape is characterized by massive telescopes, systematically scanning the entire southern sky every few nights, a revolution that promises to uncover dozens of interstellar objects each year. This leap in precision, often reaching sub-arcsecond or even milli-arcsecond accuracy, empowers astronomers to confidently exclude non-gravitational forces such as outgassing jets from influencing the object's trajectory when smaller, less accurately tracked comets would be ambiguous. When positions can be pinpointed with such detail over months of observation, even the tiniest deviations from classical Newtonian physics become detectable. This transforms our understanding. What once appeared as fuzzy dots moving through space now become precisely mapped journeys, revealing subtle nuances in their motion. Amateur astronomers, along with dedicated professional collaborations, contributed early data on the object's morphology and brightness variations, feeding this time series information into a global database. While these measurements may lack the pinpoint accuracy of large observatory instruments individually, their widespread temporal coverage is invaluable. They help characterize how the comet's brightness and appearance evolved as it warmed approaching the sun, offering insights into its activity and physical state. The orchestration of this worldwide effort exemplifies modern astronomy at its finest. An extraordinary display of collaboration across time zones and institutions. Observatories scattered across the globe maintain continuous coverage, ensuring no moment is missed as the Earth's rotation shifts each site into darkness. Radio networks coordinate pointing schedules, optimizing the collective effort. All data flows seamlessly to the Minor Planet Center, where orbital analysts synthesize these measurements, progressively refining the object's trajectory with astonishing speed. What makes this rapid progression remarkable is how it contrasts with past astronomical discoveries, which could sometimes take months or even years to verify. Thanks to advancements in computing power, automated detection algorithms, and instant communication channels, 3I Atlas's journey from initial detection to detailed orbital solution was compressed into just a matter of weeks. An impressive feat made possible by the technological ecosystem of modern science. The extraordinary precision achieved by this expansive, coordinated global network serves as the foundation for the remarkably tight constraints placed on non-gravitational accelerations affecting interstellar objects like 3 Atlas. When thousands of positional measurements are recorded with accuracy down to just a few milli-arcseconds over several months of diligent observation, even the tiniest deviations from expected purely gravitational trajectories become statistically meaningful. These deviations, though physically minuscule, can be detected with confidence, transforming what might once have been dismissed as measurement noise into significant data points that challenge our understanding of celestial mechanics. However, achieving such precision does not come without its caveats, a fact that diligent scientists always acknowledge. The residual limits, small discrepancies between the observed positions and the predictions based solely on gravity, serve as constraints on how much the actual trajectory can differ from a gravitational model. These residuals do not directly reveal the object's mass. Rather, they set bounds on the acceleration parameter attributable to non-gravitational forces. When this parameter is combined with sophisticated gas flow models, it informs the controversial estimates of the minimum mass, often termed the mass floor, necessary to account for the observed activity. The relationship between the limits on observed acceleration and the inferred mass relies heavily on several key assumptions. These include the rates at which gas sublimates from the object's surface, the escape velocities of gases leaving the nucleus, and the efficiency with which momentum is transferred from outgassing jets to the nucleus itself. Altering any of these assumptions, say, increasing the gas production rate or adjusting the escape velocity, can significantly change the resulting mass estimates. This sensitivity underscores the importance of careful, nuanced modeling when translating precise positional data into physical properties. While the Global Telescope Network provides measurements of extraordinary precision, converting these positional residuals into concrete physical characteristics of the object demands robust theoretical modeling. Despite these complexities, the achievement itself warrants high recognition. Detecting such minute acceleration limits pushes ground-based astrometry to its practical limits, effectively transforming Earth into a colossal planet-scale observatory, its baseline distances spanning continents. Each observatory contributing its unique perspective and measurement capabilities to a collective effort far exceeding the reach of any single facility. This collaborative enterprise exemplifies how data quality can now facilitate tests of fundamental physics that were impossible just a few decades ago. When positional measurements reach the extraordinary sensitivity needed to detect accelerations on the order of billionths of a meter per second squared, celestial bodies like comets and asteroids are no longer merely test masses obeying Newtonian gravity. They become laboratories for probing the nuances of momentum conservation, outgassing dynamics, and the intricate interplay between thermal physics and orbital mechanics. Such observational sophistication underpins the formidable claims made regarding 3 Atlas's anomalous behavior. Indeed, the precision of the data constrains the non-gravitational acceleration with a level of certainty that ranks among the highest ever achieved for any object within our solar system, whether interstellar or native. When measurements are this refined, they demand serious, rigorous theoretical interpretation. Unexpected results are no longer mere anomalies, but signals that challenge established models and invite deeper inquiry. Looking ahead, the global network of observatories, which has demonstrated its capability in monitoring 3 Atlas, offers a glimpse into the future of astronomy. The increasing integration of coordinated surveys, rapid response observation protocols, and ultra-precise astrometric techniques will soon become routine tools, not only for studying interstellar visitors but also for tracking near-Earth objects, assessing potential hazards, and understanding the subtle dynamical evolution of our solar system. Yet, amid these groundbreaking measurements, astronomers encountered an even more perplexing phenomenon, something that defied expectations based on classical comet physics. The images captured by the observatory network unveiled a puzzling feature, a tale that seemed to point in the wrong direction, an anomaly that would soon be termed the coma paradox. The very first of these startling observations was made on July 21st, when the Hubble Space Telescope's imaging halted scientists in their tracks. revealing a strange and unexpected morphology that challenged conventional understanding of cometary activity. Rather than displaying the typical cometary visage, an identifiable bright nucleus trailing a luminous tail of dust streaming outward from the sun, 3I Atlas presented observers with a strikingly different appearance. A teardrop-shaped cocoon cloaked in a pronounced glow directed toward our star. This forward-facing brightness, known as an anti-tail, posed a significant challenge to fundamental expectations about how comet debris behaves in the vast expanse of interplanetary space. Traditionally, comet tails point away from the sun, shaped by the relentless push of solar wind and the pressure of photons, an astronomical signpost so reliable that ancient Chinese astronomers once used comet orientations as celestial compasses to navigate the sky. When a tail appears to point toward the sun, it triggers a mental scramble in our understanding, forcing us to reconcile this unusual image with the basic principles of physics. Fortunately, anti-tails are not entirely unheard of within our solar system. They can result from specific viewing geometries, when Earth's position in its orbit creates an illusion of material flowing sunward, or from atypical dust grain dynamics, where larger particles follow ballistic paths that differ from the fine dust swept away by radiation pressure. Yet in the case of 3I Atlas, the persistent and prominent forward glow was extraordinary, standing out as a particularly unusual phenomenon. Recent scientific modeling efforts have shed light on this peculiar appearance, explaining it through a combination of sublimating grain physics and perspective effects. As icy, dust-rich particles escape the nucleus, they don't simply drift away passively. They continue to sublimate, transforming directly from ice into vapor while traveling outward. Under certain viewing angles, this ongoing sublimation can produce the illusion of a sunward feature, creating an apparent glow pointing toward the sun. The mathematical frameworks support these explanations, but the visual impact remains startling, challenging the familiar image of a comet with a tail trailing behind in the opposite direction of the sun. Throughout July and August of 2025, telescopic observations tracked the evolution of this forward glow. Remarkably, it persisted over weeks, not merely a fleeting geometric illusion that would vanish with changing viewpoints or conditions. Instead, multiple observatories recorded this prominent sunward feature, indicating that it stemmed from genuine physical processes occurring on or near the comet. Later observations, notably from Gemini South on August 27th, revealed an added layer of complexity. A more conventional anti-solar tail began to emerge as the object warmed while approaching perihelion, the closest point to the sun in its orbit. Initially, the comet exhibited primarily forward scattering, where sunlight reflected off dust grains directed their brightness toward us, making the sunward glow dominant. As the comet continued to heat up, its morphology evolved, developing the classic dual-tail structure with material streaming in both directions, toward and away from the sun. This dynamic transformation is significant because it influences how we interpret the comet's brightness, the distribution of dust and gas, and the precise location of its photometric center, the point that defines its observed brightness profile. This distinction is crucial for astrometric measurements, which track the comet's position based on the brightness-weighted centroid. If the structure of the coma, the cloud of gas and dust enveloping the nucleus, shifts or changes systematically, it can introduce biases into the orbital solutions. Such shifts could potentially mimic or conceal subtle non-gravitational forces acting on the object, forces that might originate from outgassing jets or other activity. The challenge, therefore, lies in disentangling genuine orbital dynamics from artifacts caused by the apparent displacement of the comet's brightness center. In essence, the evolving morphology of 3I Atlas, especially the prominence of its sunward glow, introduces complexities in accurately calculating its trajectory. Systematic changes in the distribution of dust and gas can influence where the comet appears to be located in the sky, potentially leading to misinterpretations of its motion if not carefully accounted for. Recognizing and correcting for these photometric artifacts is vital in understanding whether the comet's movement is purely gravitational or if subtle non-gravitational influences are at play. A meticulous examination of these phenomena is essential to prevent misconceptions about the object's true mass and its motion through space. In the realm of solar system comets, anti-tails, those striking features pointing toward the sun, are generally well understood, arising from established physical processes such as dust and gas dynamics combined with the vantage point of observation. However, the early and persistent appearance of a sunward glow in the case of 3I Atlas ventures into less familiar territory, prompting scientists to consider whether conventional models of dust behavior, viewing angles, and scattering effects can fully account for what is observed, or if more exotic mechanisms might be at play. Adding to the complexity of this morphological puzzle are the chemical signatures detected through advanced spectroscopy. The James Webb Space Telescope revealed an outgassing rich in carbon dioxide, indicative of active sublimation processes. Meanwhile, observations from the Very Large Telescope uncovered emission lines corresponding to cyanogen and nickel, yet notably lacked signals from iron. This unusual chemical combination, an abundance of carbon dioxide paired with nickel emissions but an absence of iron, paints a distinctive chemical portrait that does not align with typical solar system comet profiles. While nickel emissions are not unprecedented in cometary spectra, the absence of iron signals alongside nickel lines raises intriguing questions about the underlying physical and chemical processes. In most astronomical contexts, these metals tend to appear together because they originate from similar nucleosynthetic pathways and are usually found within comparable chemical environments. The selective presence of nickel suggests either formation conditions that are highly unusual, perhaps involving unique mineralogy or organic compounds, or the operation of exotic release mechanisms that differ from standard sublimation processes. These chemical anomalies might be directly linked to the observed morphological peculiarities, especially the anti-tail. Variations in dust grain composition, size, and sublimation dynamics could lead to the formation of dust populations with different optical properties and dynamical behaviors than those typically seen in comet debris. For example, if 3I Atlas contains metal-rich minerals or organic compounds with distinct sublimation characteristics, their differential sublimation could produce dust particles that respond differently to solar radiation pressure, influencing the formation and appearance of features such as anti-tails. To help the general audience grasp these concepts, visual explanations prove invaluable. Imagine animated vectors that illustrate some particles moving in one direction while the observable tail points in another, with perspective effects demonstrating how the viewing angle can invert the apparent relationship between the source and the debris trail. When viewing a three-dimensional process from a fixed vantage point, geometric effects can create optical illusions that challenge our intuitive understanding. For instance, the brightness glow observed in the sunward direction could result from forward scattering, where dust grains with specific sizes and compositions preferentially scatter sunlight toward the observer rather than away from the sun. This forward scattering effect can produce bright features that seem to defy basic comet physics, suggesting that the particles are acting as tiny optical mirrors, redirecting sunlight in a way that enhances the brightness in the observer's direction. However, interpreting these morphological features demands careful application of scattering theory and a solid understanding of dust particle properties. Although anti-tails have been documented in solar system comets for decades, Their existence has not fundamentally altered our comprehension of dust and gas dynamics in cometary environments. The prominent and enduring sunward glow in 3I Atlas might simply indicate more vigorous activity or the presence of dust with unusual properties, rather than revealing entirely new physics. Nevertheless, these observations underscore the necessity of cautious interpretation and further investigation to unravel the true nature of this enigmatic interstellar visitor. The delicate balance between dust and gas within interstellar objects plays a pivotal role, not only in shaping their visible appearance but also in the critical calculations used to estimate their mass through momentum transfer. Should 3I Atlas emit a proportionally greater amount of dust relative to gas than typical comets, or if its dust grains differ significantly in size distribution or composition, this could fundamentally alter the relationship between the observable activity, such as brightness and tail morphology, and the expected non-gravitational forces acting upon it. To unravel this complex interplay, scientists must synthesize observations spanning multiple wavelengths and employ a variety of techniques. Visible light imaging, for instance, reveals how dust particles scatter sunlight and provides insights into the morphology of the coma and tail structures. Infrared spectroscopy, on the other hand, maps the emissions of gases and measures their thermal properties, offering clues about the composition and temperature distribution of sublimating volatiles. Radio observations can sometimes detect specific molecular transitions, allowing researchers to directly trace the rates of gas production and better understand the physical processes driving outgassing. Combining these diverse data sets into a coherent physical model presents a formidable challenge, engaging both observational astronomers and theoretical astrophysicists alike. The time series data gathered by instruments such as the Hubble Space Telescope, Gemini Observatory, and other facilities document the morphological evolution of 3I Atlas as it approaches the Sun. This evolution is crucial because it reflects the activity of different volatile species, sublimating at varying distances, temperatures, and rates. For example, water ice begins to sublimate actively around 3 astronomical units from the Sun, while carbon dioxide requires much greater distances to become active, and other more exotic species respond only at their characteristic cold temperatures. This chemical evolution should be observable through correlated morphological changes. Different gases entrain dust in distinct ways, leading to variations in the appearance and structure of the coma and tail over time. The continued evolution of 3I Atlas's appearance throughout the observation period suggests ongoing sublimation processes that adapt dynamically as thermal conditions shift with changing orbital geometry. As it moves closer to the Sun, increasing solar heating triggers a series of sublimation events, each influencing dust entrainment and tail morphology. To illustrate this, consider a visual metaphor. It appears as though the comet is snowing toward the Sun. However, this mental image challenges our everyday experience of how debris should flow in response to external forces. Typically, comet tails point away from the Sun, pushed by solar wind and radiation pressure. So seeing a tail point sunward, the so-called anti-tail, strikes us as counterintuitive. This anti-tail phenomenon exemplifies how 3I Atlas seems determined to challenge our fundamental assumptions about matter's behavior in the space environment. From its anomalously high mass to its peculiar chemical signature and its unusual tail morphology, each new observation adds layers of complexity rather than clarity to our understanding of this interstellar visitor. A particularly troubling question arises if the preliminary estimates about Atlas's mass are correct. Where are all the smaller interstellar objects we expected to have discovered first? This leads us into the realm of what is often called the uncomfortable implication, a puzzle that keeps astronomers awake at night. If 3I Atlas truly possesses a mass of 33 billion tons or more and a nucleus spanning at least 5 kilometers, it represents an extreme outlier in our current understanding of interstellar object demographics. Under standard models, such a colossal object should be extraordinarily rare, and its existence raises fundamental questions about the distribution and abundance of smaller bodies that should have preceded it in our observational record. From a logical standpoint, we would expect to have detected dozens, if not hundreds, of smaller interstellar visitors before encountering such a massive specimen. The reasoning is straightforward. In planetary systems, debris ejection mechanisms, whether through gravitational scattering, stellar flybys, or disk instabilities, favor smaller objects being ejected more easily and more frequently than larger ones. The laws of physics suggest that smaller debris requiring less energy to accelerate to escape velocity are inherently more numerous in the interstellar medium. Such objects are easier to detect with current surveys, which are biased toward brighter, smaller bodies passing through the inner solar system. Yet here we find ourselves with 3 confirmed interstellar objects, Oumuamua, Borisov, and now Atlas, spanning a dramatic range of sizes and masses. The first, Oumuamua, was estimated at merely a few million tons, while Borisov resembled a typical comet, about 1 kilometer in diameter. Now Atlas potentially surpasses those earlier visitors by factors of 10 to 1,000 in mass, a heavyweight in a field once dominated by lightweight objects. This raises troubling questions. Are our current detection methods biased or incomplete? Are larger objects more common than previously thought? Or are we simply missing the smaller ones due to observational limitations? The apparent scarcity of smaller interstellar objects, despite the expectation that they should be vastly more numerous, poses a significant challenge to existing models of debris ejection and galactic population dynamics. This conundrum underscores the importance of upcoming surveys. Planetary systems eject debris through a variety of dynamic processes, including gravitational scattering during the tumultuous phases of planet formation, close stellar flybys that disturb and displace objects in the outer regions of a system, and instabilities within debris disks surrounding young stars. Each of these mechanisms tends to favor the ejection of smaller objects more readily than their larger counterparts. This is primarily because less massive debris requires significantly less energy to accelerate to the escape velocity necessary for leaving their parent systems. Consequently, smaller fragments are inherently more abundant in the vast expanses of interstellar space, forming a dominant component of wandering debris. Furthermore, observational biases naturally skew detection toward these smaller objects within certain size ranges. While the tiniest debris, such as microscopic dust particles, are currently beyond the reach of our detection capabilities, objects measuring roughly 100 meters to a kilometer in diameter should, in principle, be detectable when they venture into the inner regions of the solar system. As they approach the sun, they develop visible comets, with tails and coma that make them stand out against the starry background. What makes this scenario particularly intriguing is the diversity and the mass of our first 3 confirmed interstellar visitors. These objects span an astonishing range. From Oumuamua, estimated to weigh in the millions of tons, to 3I Atlas, which potentially exceeds tens of billions of tons. This vast disparity in mass among the initial detected interstellar travelers defies simple statistical expectations. Under naive assumptions, one would anticipate the discovery sequence to favor smaller, more numerous objects. Yet the observed pattern suggests otherwise. One possible explanation lies in observational selection effects. Recent wide-field surveys such as the Atlas and Catalina Sky Survey have only just begun to achieve the sensitivity and sky coverage necessary to routinely detect interstellar objects passing through our neighborhood. The upcoming Vera Rubin Observatory promises to revolutionize the field of transient astronomy, with the capability to scan the entire southern sky with unprecedented depth and frequency. It is likely that our current sampling of interstellar debris is severely incomplete, capturing only the tip of a far larger hidden population of objects. The order in which we detect these objects might be a matter of chance geometry rather than true rarity. For instance, 3I Atlas approached the inner solar system along a trajectory nearly aligned with the ecliptic plane, the same plane in which most planets orbit. This alignment makes it considerably easier to spot and track than objects arriving on highly inclined or retrograde orbits, which might pass through the solar system from more oblique angles and thus be more difficult to observe. Such a favorable geometric configuration could have effectively compensated for the low intrinsic probability of detecting such a massive interstellar object, skewing our initial discovery pattern. Alternatively, the apparent anomaly could point to gaps in our understanding of the physical mechanisms behind debris ejection. It is conceivable that certain stellar environments or evolutionary pathways tend to preferentially eject larger objects, perhaps due to specific gravitational dynamics or early system conditions. Conversely, small debris might be destroyed or dispersed more efficiently during the long voyage between stars, reducing their likelihood of reaching our solar system intact. Processes such as cosmic ray erosion, collisions with interstellar dust, or sublimation caused by stellar encounters could serve to fragment or vaporize smaller objects over millions of years, effectively thinning the population of small interstellar debris that survives the journey. The hypothesis that small objects are more fragile and prone to destruction during interstellar transit warrants serious scientific consideration. It is plausible that bodies smaller than a few hundred meters in diameter do not survive the rigors of a million-year-long voyage through the galaxy. These objects might be gradually worn away or completely obliterated by cosmic ray bombardment, thermal stresses from passing through varying stellar environments, or collisions with interstellar particles. As a result, the population of interstellar objects that eventually reach our solar system could be biased toward larger, more resilient fragments, which are better equipped to withstand the destructive processes of interstellar travel. Despite these considerations, the early detection of 3I Atlas remains statistically perplexing. Population synthesis models, advanced computational frameworks designed to match the observed distributions of asteroid belt and Kuiper belt objects, struggle to accommodate such a colossal interstellar visitor appearing so early in our discovery timeline. These models typically predict a gradual size-dependent distribution of interstellar debris, with smaller objects vastly outnumbering larger ones. The presence of such a massive body among the first three known interstellar objects challenges these conventional models, suggesting that either our understanding of ejection and survival processes needs revision, or that 3I Atlas is an extraordinary outlier, an unusual but statistically plausible exception in the broader cosmic landscape. Either our current models require significant revision, or the occurrence of a 3I Atlas-like object truly represents a rare cosmic event, one that happened to be observed during humanity's earliest and most comprehensive search for interstellar visitors. To grasp the magnitude of this puzzle, it's helpful to consider the broader historical context. The discovery of Oumuamua in 2017 marked the dawn of serious interstellar object astronomy, opening our eyes to the reality that objects from beyond our solar system can and do pass through. Then in 2019 came the detection of Comet Borisov, which behaved in many ways like familiar comets within our own planetary neighborhood, reinforcing that some interstellar visitors resemble the small, icy bodies we already understand. By 2025, the appearance of 3I Atlas brought the sample size up to 3 confirmed interstellar objects. But with such a tiny data set, Drawing broad conclusions about the demographics or population characteristics of interstellar debris is statistically meaningless. It's akin to trying to understand the distribution of human heights by measuring only 3 individuals picked at random. The sample is so small that a single outlier, a particularly tall or short person, can completely skew any inference. Excessively small samples like this risk leading us astray, making it challenging to distinguish genuine patterns from random fluctuations. Fortunately, statistical tools and survey mathematics offer a ray of hope for resolving this profound uncertainty. The Vera Rubin Observatory's Legacy Survey of Space and Time, LSST, is poised to transform our understanding. Over the next decade, it will scan the entire southern sky every few nights, systematically cataloging transient objects and providing a vast data set. If 3i Atlas is representative of typical interstellar visitors, LSST should frequently detect similar large, massive objects, enabling us to build a meaningful statistical picture. Conversely, if 3i Atlas is an extraordinary outlier, a rare statistical anomaly, LSST's extensive survey will instead uncover a plethora of smaller, more typical interstellar objects, revealing that the giant is not the norm, but a cosmic rarity. The stakes in this scientific quest stretch far beyond mere curiosity about the makeup of interstellar populations. If objects as massive as 3i Atlas are common, then our models of stellar system formation must be re-evaluated, especially the mechanisms by which such large bodies are ejected from their parent systems. Current theories mainly emphasize planetary migration and gravitational scattering during the tumultuous early phases of planetary system evolution. In these models, smaller debris, rubble and icy pebbles, are ejected more readily, and the ejection of colossal objects like 3i Atlas appears improbable without invoking more exotic processes. Should 3i Atlas prove to be genuinely anomalous, its properties could point to formation mechanisms that are more exotic or survival strategies that allow such a massive body to withstand ejection forces. This would challenge our understanding of how planetary systems evolve and shed material into interstellar space, possibly revealing processes we've yet to imagine. Exploring these mechanisms could shed light on aspects of planetary system evolution that remain elusive, even in our own solar neighborhood, such as how and when the largest planetesimals and planetary cores are expelled or survive their tumultuous birth environments. This entire conundrum links directly to the reservoir model problem in galactic astrophysics. Stars are born in dense clusters and associations where gravitational interactions between stellar systems are frequent and intense. These interactions, stellar flybys, planetary scattering, and the chaotic evolution of protoplanetary disks, are believed to scatter debris across interstellar distances. The efficiency of these processes, combined with the rate at which stars form and evolve over cosmic time, determines how many interstellar objects of various sizes should be wandering through space at any given moment. Current estimates suggest that the local interstellar medium contains billions of objects larger than 100 meters per cubic parsec. Most of these bodies, however, remain invisible to our telescopes, unless they pass sufficiently close to the sun to develop a detectable coma or reflect enough sunlight to be observed directly. The challenge then becomes connecting these theoretical population predictions with the tiny number of objects we have actually observed so far. This discrepancy underscores the importance of expanding our observational reach and refining our models to better understand the true nature and abundance of interstellar debris. Ethical storytelling entails a delicate balance. We must openly acknowledge the limits of our current understanding while simultaneously fostering enthusiasm for the discoveries that lie ahead. The mass estimates of the interstellar object known as 3i Atlas could very well be inaccurate, The population statistics we've inferred might be skewed by observational biases rather than reflecting true anomalies. As our data collection grows richer and our theoretical models become more sophisticated, some of these unsettling implications may gradually fade away, dissolving into the realm of refined knowledge. Yet paradoxically, this very uncertainty enhances the story's allure, drawing us deeper into the mysteries of the cosmos. We are witnessing a moment in astronomy when genuinely surprising observations are forcing us to reevaluate long-standing frameworks. Whether 3I Atlas turns out to be a typical representative or an extraordinary outlier, it compels the scientific community to confront fundamental questions. How does matter traverse the vast distances between stars? What do these journeys reveal about the broader processes of galactic evolution? The challenge of small sample sizes, our current limited data set, is expected to diminish over the coming decade, as improvements in survey technology and increased discovery rates yield dozens, perhaps hundreds, of interstellar visitors for analysis. Such growth in data will transform population statistics from mere speculation into robust, evidence-based inferences rooted in meaningful sample sizes. Until that time, 3I Atlas remains a puzzling ambassador from the space between stars, carrying with it invaluable clues about conditions and processes in stellar environments that are, as of now, beyond our full comprehension. Its anomalous properties, whether truly intrinsic or artifacts of measurement, serve as catalysts. They push us to pursue better observations, refine our models, and ask deeper questions about our rightful place within the cosmic ecosystem. The lingering, uncomfortable implication persists. If we are discovering massive interstellar objects before smaller ones, then crucial pieces of our understanding about how debris moves through the galaxy are missing. This raises a pivotal question. Does this gap stem from observational bias, from gaps in our theoretical frameworks, or from the presence of genuinely exotic physics operating silently in the vast uncharted spaces between stars? Before we can confidently interpret population statistics, it is essential to clarify what our current models, specifically those describing ejection mechanisms and reservoirs, actually predict about objects like 3I Atlas. This leads us to the core of the interstellar reservoir problem. Our galaxy functions as a colossal redistribution network for planetary debris, with stellar systems perpetually ejecting material into the interstellar medium. This ejected matter then becomes the source of interstellar visitors, cosmic messengers carrying information across the galaxy. To understand this cosmic recycling, we must model three primary ejection mechanisms: planet-to-planet interactions, gravitational scattering, and close stellar flybys, along with instabilities within protoplanetary disks surrounding young stars. Among these, planet-to-planet scattering currently stands as the dominant process in our theoretical frameworks. During the turbulent early stages of planetary system formation, massive bodies such as giant planets migrate through gravitational interactions. These interactions can be intense enough to fling smaller objects onto hyperbolic escape trajectories, sending them hurtling out of their home systems and into the vast interstellar void. This process resembles a cosmic billiard game, where planets act as cue balls, striking asteroids and comets with enough force to launch them into interstellar space. The physics underlying this mechanism naturally favors the ejection of smaller, less massive objects. The energy required to propel a tiny asteroid or comet is significantly less than that needed for larger bodies. During these chaotic early epochs, as planetary systems are still coalescing and dynamically unsettled, such gravitational interactions are frequent and vigorous. The resulting ejections are a continuous and vital aspect of galactic debris recycling, shaping the population of objects that eventually drift into our observational reach. In the vast theater of cosmic dynamics, The velocity at which objects are ejected from their parent systems exhibits a pronounced dependence on their mass when influenced by gravitational encounters. Specifically, lighter debris can attain escape velocity with relative ease during such interactions, as their lower mass means less energy is required to break free from gravitational bonds. For instance, a planet comparable to Jupiter can effortlessly propel kilometer-scale comets into interstellar space, leveraging the immense gravitational pull it wields. However, ejecting something as massive as the hypothetical 3I Atlas, a colossal interstellar object, demands far more precise conditions and a significantly greater transfer of energy. One alternative pathway for ejecting such large bodies involves stellar flybys, especially significant in the tumultuous environments of young stellar clusters. These regions are densely packed with nascent stars forming in close proximity, and when another star ventures within a few hundred astronomical units of a planetary system, its gravitational influence can have destabilizing effects. This close approach can scatter objects in the outer regions of the system onto hyperbolic escape trajectories, effectively ejecting them into interstellar space. The efficiency of this process hinges on several factors: the velocity of the passing star, the closest approach distance during the flyby, and the specific architecture of the target system's outer regions. In particular, stellar flybys are capable of ejecting larger bodies than those expelled by planetary interactions alone. This is because stars often outweigh planets by significant factors, sometimes by hundreds or even thousands, making their gravitational influence far more potent. A flyby involving a star with a mass similar to our Sun could, in principle, launch objects weighing billions or tens of billions of tons into interstellar space. Such a mechanism presents a plausible explanation for the origin of massive visitors like the 3I Atlas, suggesting that the ejection of enormous debris is not only possible but perhaps common under certain astrophysical conditions. Beyond stellar flybys, the early phases of planetary system formation offer yet another route: disk instability. During these formative stages, before planets have fully coalesced, the protoplanetary disk, a rotating mass of gas, dust, and planetesimals, is susceptible to gravitational instabilities. These instabilities can give rise to spiral density waves and other non-axis symmetric structures within the disk, which can scatter embedded objects outward. This process predominantly occurs within the first few million years of a star's life, a period during which the disk still retains a substantial amount of mass and gas, providing the raw material and conditions necessary for such dynamical interactions. However, a significant challenge in understanding the origins of interstellar objects lies in predicting which ejection mechanism dominates in various stellar environments. Different stellar populations, such as young clusters versus isolated field stars, metal-rich versus metal-poor systems, or binary versus solitary stars, are likely to produce distinct ejection signatures and debris characteristics. The diversity of environments complicates the task of modeling and interpreting observed data. Currently, observational constraints are painfully limited. Confirmed interstellar visitors remain few. Examples include Oumuamua, 2I Borisov, and the recent candidate 3I Atlas. With such a sparse data set, uncertainties about the demographics of these objects are vast, spanning orders of magnitude. In such a small sample, outliers can disproportionately skew the perceived characteristics of the population, rendering statistical inferences nearly meaningless. Nevertheless, the upcoming era of interstellar object astronomy promises dramatic progress. The Vera Rubin Observatory, now entering its commissioning phase, offers a glimpse into this future. Equipped with a wide-field camera and a rapid survey cadence, it is poised to detect dozens, perhaps hundreds, of interstellar visitors each year. This influx of data will transform our understanding from mere speculation into a robust empirical foundation, enabling detailed statistical analyses of their origins, sizes, and compositions. An astronomical revolution in the making. Current models attempt to link the processes responsible for ejecting these objects to the characteristics we observe when they pass through our solar system. By simulating the buildup of interstellar debris over galactic timescales, these reservoir models aim to shed light on the broader population and distribution of interstellar objects, providing crucial insights into their formation and ejection mechanisms across the galaxy. The processes governing star formation rates, the dynamics within stellar clusters, and the architectures of planetary systems all play crucial roles in shaping the distribution of material, ranging across various sizes, that drifts through our local interstellar neighborhood. These interconnected factors feed into sophisticated models that generally forecast a vast predominance of smaller objects in the interstellar medium. The precise way in which the number of objects scales with size hinges heavily on the specific mechanisms by which debris is ejected from planetary systems and the survival probabilities of these fragments during their interstellar journey. Most models favor a steep size distribution, implying that kilometer-sized objects are exceedingly rare when compared to their smaller 100-meter counterparts. This steep gradient in population distribution becomes especially significant when considering the so-called disk lifetime problem. Protoplanetary disks, vast rotating bands of gas, dust, and debris surrounding young stars, tend to dissipate within a relatively short window of 5 to 10 million years. This dissipation occurs primarily through processes like photoevaporation, where intense stellar radiation effectively blows material away, and accretion, where matter spirals inward onto the star itself. Such a constrained timeline imposes strict limits on how much material can be ejected during the early disk phase compared to later epochs dominated by planetary scattering. If the ejection of massive objects, such as the giant fragments hypothesized in the case of interstellar visitors like 3 Atlas, is driven significantly by disk instabilities, then these mechanisms must operate with remarkable efficiency during this brief period. It follows that such large objects would need to form and be expelled before the parent disk fully dissipates, thus placing tight constraints on plausible formation and ejection scenarios. Addressing the apparent paradox of population sizes, the observation that such enormous interstellar objects seem to be more common than models would naturally predict, requires considering several potential resolutions. One possibility is survivorship bias, where the population we detect is skewed because smaller objects are more likely to be destroyed or eroded during their interstellar transit. Over millions of years, cosmic ray bombardment, sublimation caused by random stellar encounters or collisions with interstellar dust could disproportionately eliminate these smaller fragments, leaving only the most robust massive bodies to reach our solar system intact. If only these resilient giants survive such hazardous journeys, then the population we observe would be inherently biased toward larger sizes. Another factor influencing detection statistics is the geometry of observation itself. Objects approaching from certain directions, particularly near the ecliptic plane where most surveys focus, stand a better chance of being detected because their paths are more accessible to current telescopic systems and they remain visible over longer periods. Conversely, visitors on highly inclined or retrograde orbits might be systematically underrepresented simply because they are less favorably positioned for observation from Earth-based observatories. Additionally, if some objects contain unusually rich dust comas, clouds of fine particles surrounding the nucleus, they could appear brighter than their actual size would suggest, making them detectable at greater distances than similarly sized but less active counterparts. Specifically, if an object like 3 Atlas produces more dust per unit of its nuclear surface area than typical comets, it could have been observable from much farther away. This dust-rich environment would enhance its brightness artificially, leading to a detection bias favoring such active, dust-laden visitors. Consequently, the current understanding of the interstellar population must consider these selection effects. Most importantly, the prevailing scientific stance remains cautious. The apparent anomalies, such as the disproportionate size or brightness of 3 Atlas, are viewed as prompts for acquiring more and better data, rather than concluding definitively that the population of interstellar objects is skewed toward larger bodies. Scientists see these observations as an invitation to refine models and gather more evidence. The observed data, while intriguing, are best regarded as preliminary clues that require further validation before rewriting the fundamental assumptions about the distribution and nature of interstellar debris. The current collection of interstellar objects, just 3 identified visitors, lacks the statistical robustness necessary to draw definitive conclusions about the broader population. Such a limited sample size makes it impossible to reliably constrain the models that describe the demographics of objects wandering between the stars. Claims suggesting the existence of unusual patterns or anomalies in the distribution of these visitors demand an extraordinary level of evidence, and at present our data simply do not meet that high threshold. Despite this, the underlying theoretical challenge remains significant and compelling. Should future surveys reveal that large, massive interstellar objects are encountered more frequently than current reservoir models predict, then those models will need to be revised accordingly. Such revisions could involve postulating more efficient ejection mechanisms capable of launching larger bodies into interstellar space, or proposing that the source stellar systems produce these enormous objects at a higher rate than previously thought. The importance of understanding these processes extends well beyond mere population counts. They are fundamental to deciphering the physics of planetary system formation and evolution across the galaxy. Every debris fragment that drifts through interstellar space carries with it a record, an imprint, of the conditions and environments in which it originated, spanning billions of years of galactic history. To make sense of these clues, scientists employ population synthesis models that aim to connect the observable characteristics of interstellar visitors with the complex physical processes that produce them. These models incorporate a variety of factors, including the rates at which stars form, the dynamical interactions within stellar clusters, the architectures of planetary systems, and the efficiencies with which objects are ejected from their birthplaces. By simulating these processes, theorists can estimate how many objects of different sizes should pass through the inner solar system over a given period. Currently, predictions from these models vary widely, reflecting significant uncertainties rooted in the assumptions about underlying physics. Some frameworks suggest that we should encounter objects larger than 100 meters at a rate of roughly 1 per year, while others propose rates that are either an order of magnitude higher or lower. The discovery of 3 Atlas, along with its predecessors, marks the first step toward empirically constraining these theoretical predictions. In essence, these interstellar objects serve as a bridge, connecting local observational data to the vast galactic-scale processes that operate over billions of years. Each visitor is a sample taken from this immense population, carrying potential insights into the conditions of formation, the mechanisms of ejection, and the survival probabilities that govern their journey through interstellar space. Conditions we will likely never witness directly. As detection technology improves and the sample size of observed interstellar objects grows, the field of population statistics will transition from mere speculation to precise quantitative science. The peculiarities and anomalies initially observed around Atlas might ultimately turn out to be statistical fluctuations, early data quirks that will be smoothed out with a larger data set. Or they could reveal genuine surprises, fundamentally altering our understanding of how matter moves and is distributed across the space between stars. Before reaching such conclusions, however, astronomers first face an intriguing challenge: deciphering the unexpected chemistry signal that Atlas delivered, specifically the nickel emissions detected without the accompanying iron signals. This issue, known as the nickel without iron mystery, forms a crucial part of Part 7 of this ongoing investigation. High-resolution spectroscopy using the Very Large Telescope revealed something genuinely perplexing in Atlas's coma. Multiple emission lines associated with nickel were blazing prominently in the infrared spectrum, yet iron remained conspicuously absent from the same spectral data. This unexpected chemical asymmetry challenges our basic assumptions about how metals behave and emit in cometary environments, adding yet another layer to the list of properties that make Atlas an anomaly. The observation itself is straightforward, spectroscopic detection of specific emission lines, but it is striking because of what it implies about the object's composition and the processes occurring within its coma. During August 2025, the Very Large Telescope's high-resolution spectrographs revealed several atomic transitions of nickel within the wavelength range of 700 to 900 nanometers. These spectral lines emerged distinctly above the noise background, allowing scientists to perform precise quantitative analyses of nickel emission rates and to map their spatial distribution within the comet's coma. Intriguingly, neighboring spectral regions, where astronomers anticipated detecting iron lines, showed no such signals at all. The absence of iron lines was not merely a matter of signals being too weak to observe. Instead, the spectral data indicated that iron emission was effectively below the detection thresholds established for comets at comparable distances from the Sun. This stark lack of iron signals signifies a genuine chemical anomaly, an unexpected and peculiar compositional feature that invites careful explanation. Placing this anomaly into broader context accentuates its significance. In most astronomical environments, iron and nickel tend to appear together, owing to their shared origin in similar nucleosynthetic processes, those that occur within stellar interiors, and their tendency to form comparable compounds in meteoritic and cometary materials. Their joint presence is a well-established pattern, a kind of chemical signature of common stellar production. To find nickel in abundance while iron remains conspicuously absent is akin to discovering a dense forest dominated solely by oak trees, with no maple trees present, in a region where both species are known to coexist naturally. This analogy underscores how unusual and unexpected the chemical profile of 3I Atlas is. Further analysis based on spectroscopic data from the Very Large Telescope indicated that the production rates of nickel increased steeply as the comet approached the Sun. Specifically, both nickel and cyanogen emissions intensified dramatically with decreasing heliocentric distance, following power law relationships with exponents roughly around -8 to -9. Such a rapid increase in brightness points to a process with a pronounced temperature dependence, meaning that as the nucleus surface warms due to solar heating, some physical or chemical mechanism becomes suddenly much more efficient at releasing these species into the gas phase. This steep scaling suggests that the emission mechanism operates near a critical temperature threshold, where a small increase in temperature triggers a disproportionately large release of nickel atoms into the coma, making their spectral lines more prominent. Understanding the mathematics of this temperature dependence offers vital clues about the underlying physical and chemical processes at play. Conventional comet chemistry provides several potential explanations for the observed metallic emissions, but none perfectly aligns with the pattern seen in 3I Atlas, particularly the selective abundance of nickel without corresponding iron. For example, direct sublimation of metal-rich minerals typically necessitates extremely high temperatures, much greater than those attained at the comet's maximum solar distance during the observations. This discrepancy implies that a more subtle or complex process must be responsible. One plausible mechanism is photon-stimulated desorption. Solar ultraviolet radiation can break chemical bonds on the comet's surface, releasing atoms or molecules that would otherwise remain tightly bound, an effect seen in laboratory experiments on terrestrial minerals. If 3I Atlas contains nickel-bearing compounds that are especially susceptible to this photon-induced liberation, while iron-bearing phases are more resistant and remain intact, it could explain the observed selective emission. Alternatively, other hypotheses involve thermolysis, thermal decomposition of organic metallic compounds or metal carbonyl complexes potentially present in the nucleus. These processes, driven by surface heating, might selectively release nickel atoms, further contributing to the peculiar chemical signature observed. Certain materials within the comet's makeup can break down at relatively modest temperatures, releasing metal atoms into the surrounding environment through chemical decomposition rather than the direct sublimation of refractory minerals. In this context, if nickel tends to form more volatile compounds than iron within such interstellar environments, it's conceivable that this differential volatility could lead to the observed chemical abundance patterns, where nickel appears unexpectedly enriched compared to iron. Adding further complexity to this chemical puzzle is the detailed spectroscopic data from the James Webb Space Telescope, which detected a significant presence of carbon dioxide with an unusually high ratio of carbon dioxide to water. This distinctive ratio suggests that the comet formed in extremely cold regions beyond the so-called carbon dioxide snowline, an outer zone in stellar systems where temperatures are low enough for carbon dioxide to freeze and condense into ice. When combined with the prominent emissions of nickel, this chemistry points toward an origin in environments vastly different from the typical birthplaces of solar system comets, which usually form closer to their parent stars. These signatures of chemistry and elemental composition imply that the comet might have originated in the outermost regions of its stellar system, where temperatures are sufficiently low for exotic ice phases and metal-rich compounds to condense and survive. The journey through interstellar space would then serve as a preservative, maintaining these primordial chemical fingerprints from alien stellar environments that existed billions of years ago. However, it is crucial to emphasize what this chemistry does not prove, despite some media speculation suggesting otherwise. Some commentators have drawn attention to the presence of nickel without accompanying iron, noting that such a pattern resembles certain industrial alloys and proposing the possibility of technological or artificial origins. Yet this leap in reasoning is unsupported by the spectroscopic evidence at hand. Metallic emissions observed in cometary spectra are well understood through atomic physics, which explains how atoms and ions emit light at characteristic wavelengths, rather than being indicative of engineered or artificial materials. This highlights the importance of media literacy in interpreting scientific findings. Unfortunately, many second-tier websites and social media platforms have amplified narratives implying that nickel signals an artificial or extraterrestrial technology, despite the absence of peer-reviewed evidence supporting such claims. The scientific team working with the Very Large Telescope, VLT for instance, has presented their spectroscopic results as intriguing examples of unusual but entirely natural chemistry, distinguishing these from unfounded claims of manufactured objects disguised as comets. This distinction underscores a broader challenge, differentiating genuine scientific anomalies which merit further investigation from sensationalized misinterpretations that distort public understanding of how astronomy operates. While unusual chemistry in a comet is certainly worthy of detailed study and explanation, it does not automatically indicate artificial origin. The universe is replete with natural processes capable of producing unexpected elemental abundance patterns. Historical parallels from our own solar system support this perspective. Several comets have exhibited metal emissions with atypical ratios that initially puzzled researchers but were later explained through known physical phenomena such as grain composition, temperature-dependent sublimation, or photochemical processing. The scientific method remains our best tool for navigating these mysteries. It involves proposing hypotheses, testing their predictions through observations and experiments, and refining explanations as new data emerges. For example, the nickel emission lines observed in the comet's spectrum provide key quantitative constraints, allowing scientists to estimate gas production rates, kinetic temperatures, and the physical conditions within the comet's coma. The widths of spectral lines reveal information about thermal broadening and bulk motion velocities, while the ratios of line intensities help determine excitation conditions and the density of the emitting material. All this data feeds into detailed physical models of the coma's structure and its evolution over time, helping researchers understand the processes governing the release and distribution of materials as the comet warms approaching the Sun. In essence, these spectroscopic insights form a critical foundation for unraveling the complex chemistry and physics at play in this extraordinary interstellar traveler. A vivid illustration of the spectroscopic data offers clarity on what the Very Large Telescope, VLT, truly observed in this remarkable interstellar visitor. Visualize a spectrum plotted with wavelength along the horizontal axis and brightness on the vertical, revealing how specific elements manifest in the light signature. In this spectral landscape, the emission lines of nickel stand out as sharp, distinct peaks at particular wavelengths, each one corresponding to the characteristic photons emitted during atomic transitions. These peaks serve as unmistakable fingerprints indicating the presence and abundance of nickel in the comet's coma. Conversely, the spectral regions where iron emission lines are expected to appear, lines that should manifest at predictable wavelengths based on atomic physics, are strangely silent. Instead of clear signals, these regions are dominated by a background of noise, with no prominent peaks emerging from the data. This absence of iron lines, despite the detectable nickel emissions, deepens the mystery surrounding the comet's chemical makeup. Beyond the spectral signatures themselves, the spatial distribution of nickel emissions within the coma offers additional insights into the underlying release mechanisms and transport processes at work. If the nickel originates from localized, discrete active regions on the nucleus's surface, perhaps spots where sublimation or outgassing is particularly vigorous, then the emission should display corresponding spatial structures when observed with high enough resolution. High-resolution spectroscopic imaging would reveal concentrated patches or distinct hotspots of emission, aligned with these active zones. Conversely, if the nickel is produced through a more diffuse process, such as grain processing distributed throughout the coma, the emissions would appear more evenly spread, lacking any specific localization. Currently, the available observations lack the spatial resolution necessary to map these detailed structures within the coma, leaving the precise distribution ambiguous. However, the forthcoming generation of extremely large telescopes, whose construction is progressing rapidly, promise to provide unprecedented spatial and spectral resolution. These advancements will enable astronomers to distinguish between the scenarios of localized versus distributed nickel release, offering a clearer picture of the physical processes shaping this interstellar object. Monitoring how the nickel emissions evolve over time as 3I Atlas approaches perihelion will be pivotal for testing proposed release mechanisms. If photodissociation, the process where solar ultraviolet radiation breaks bonds and releases atoms, dominates, then the rate of nickel emission should closely follow fluctuations in solar flux intensity. As the comet draws nearer to the Sun, increased solar radiation would enhance nickel release, resulting in a correlated rise in emission rates. Alternatively, if thermal processes, such as surface heating and subsequent sublimation, are the primary driver, then the emission rates should track the surface temperature evolution. In this case, there would be a measurable delay, corresponding to the time required for thermal diffusion through the surface layers before increased sublimation occurs. These spectral observations extend beyond mere chemical curiosity. They serve as direct probes into the abundance of refractory elements, those resistant to melting or vaporization, and the chemical processing occurring within the comet's environment. Such data shed light on the primordial compositions preserved from the conditions of stellar system formation, both in our own early solar system and in distant alien planetary environments. The peculiar case of nickel emissions without accompanying iron exemplifies how 3I Atlas continues to defy straightforward expectations across multiple observational domains. From its anomalously large mass to its enigmatic morphology and distinctive chemistry, this interstellar visitor persistently challenges the foundational assumptions of astronomy. Historically, such anomalies have been catalysts for scientific progress, compelling researchers to revisit and refine their models, question core principles, and develop more comprehensive theoretical frameworks. Whether ultimately explained through conventional physics or revealing entirely new phenomena, the unusual properties of 3I Atlas are already expanding our understanding of interstellar chemistry and the processes governing comet evolution. Such mysteries have historically sustained scientific debates, like the years-long discussions surrounding Oumuamua, generating numerous theoretical papers and prompting follow-up observational campaigns. These puzzles serve as vital motivators, driving the development of cutting-edge instruments, more detailed observations, and increasingly sophisticated models that deepen our grasp of the complex and dynamic universe in which we reside. But what are the implications when someone suggests that the growing list of irregularities points to an entirely different origin, one rooted in advanced technology rather than natural cosmic processes? This question ushers us into Part 8, the technological hypothesis. The idea that 3I Atlas might be of artificial origin does not arise from a single anomaly, but rather from a convergence of peculiar traits that collectively challenge the conventional understanding of natural interstellar objects. Proponents highlight statistical improbabilities in its orbital geometry, the inconsistency of its observed mass with expected non-gravitational forces, the precise alignment with the plane of our solar system, and the unusual chemical signatures detected, all of which could be circumstantial evidence hinting at an engineered, rather than purely natural, origin. One of the most compelling points supporting this hypothesis involves the object's approach trajectory. 3I Atlas approaches our solar system with an orbital inclination of merely about 4.1 degrees relative to the ecliptic, the plane in which most planets orbit the Sun. Statistically, such a close alignment with the planetary plane is rare among interstellar arrivals, occurring randomly in only about 1 out of every 500 objects arriving from arbitrary directions in space. While not outright impossible, this near alignment raises eyebrows among researchers who track the statistical distribution and characteristics of interstellar visitors. Among the most vocal advocates for considering technological explanations is Harvard astronomer Avi Loeb. His stance is rooted firmly in scientific methodology rather than speculative conclusions. Loeb emphasizes the importance of rigorous probability calculations, weighing various natural scenarios against the possibility of artificial origins when conventional physics cannot fully account for the observed phenomena. His approach involves systematically assessing whether the anomalies can be explained through known natural processes, or if they are better explained by the intervention of an intelligent, possibly extraterrestrial technology. The upcoming opportunity for a close encounter. When NASA's Juno spacecraft could potentially intercept 3I Atlas during its passage near Jupiter on March 16, 2026, adds a practical urgency to these theoretical debates. Several papers authored by Loeb, Hibbard, Crowell, and colleagues outline ambitious yet technically challenging mission concepts for redirecting existing spacecraft to gather definitive in situ data. Achieving such a rendezvous would involve complex orbital maneuvers, precise thruster burns close to Jupiter, to alter Juno's trajectory with the goal of intercepting the interstellar object. These maneuvers push current engineering limits, requiring meticulous timing, exact calculations, and optimal fuel use. Nonetheless, the proposals reflect a genuine scientific ambition to obtain direct close-up data rather than relying solely on distant telescopic observations to resolve whether this object is a natural cosmic wanderer or something more extraordinary. The estimates of the object's mass further fuel the hypothesis of artificiality. If 3I Atlas indeed weighs tens of billions of tons, an amount consistent with a very large artificial construct, yet shows active outgassing with minimal orbital perturbation, it becomes difficult for conventional comet physics to explain its behavior. Typically, a body of such mass, when releasing gas, should experience a detectable recoil, an orbital nudge, due to the momentum transfer. The absence of such an effect despite observable activity suggests something unusual. Perhaps controlled propulsion or some form of engineered stabilization. Advocates of the artificial origin theory suggest that a controlled propulsion system could reconcile this disconnect. It might be that the object's apparent activity, jets of gas, dust, or plasma, are not merely natural sublimation phenomena, but part of an advanced, perhaps even deliberate maneuvering system designed to mimic natural activity while maintaining a stable trajectory. Natural explanations, however, still exist. Dust-driven forward scattering, for instance, could produce the sunward glow observed without invoking exotic physics, simply by the way dust particles reflect and scatter sunlight. Similarly, the chemistry of the object, which appears to be rich in carbon dioxide ice, might suggest formation in a cold, distant region of its parent stellar system, potentially a place where unusual volatile compounds could develop. These activity patterns could well be explained within the framework of natural cometary processes, albeit with some atypical composition or environmental conditions. In essence, the debate hinges on whether the peculiarities observed are best explained by an extraordinary natural object or by an artifact of intelligent design. This ongoing discussion underscores the importance of gathering more data through in situ inspection, targeted missions, and advanced modeling to conclusively determine the true nature of 3I Atlas. Variations in grain size distributions or compositions could significantly influence how efficiently momentum is transferred between the escaping gases and the solid nucleus of an interstellar object. Such differences may alter the dynamics of outgassing, potentially leading to discrepancies in expected recoil forces. As a result, the debate surrounding extraordinary claims, such as the assertion that an object might be artificially propelled, becomes particularly sensitive to the quality and interpretation of evidence. While the absence of specific ion emissions or the detection of unexpectedly small accelerations might seem suggestive to some observers, these factors alone do not serve as definitive proof of artificial intervention or propulsion. In the realm of scientific validation, claims that challenge conventional understanding demand extraordinary evidence. This could include clear, resolved imagery revealing structures that appear manufactured or engineered, radar signatures that do not match any known natural materials, or trajectory deviations that cannot be explained by outgassing physics alone. Such robust, multifaceted evidence is essential to substantiate assertions of artificial origin and to distinguish them from natural phenomena. The challenge of effective communication becomes apparent when translating scientific uncertainty into the broader public discourse. Headlines that describe an interstellar object's perihelion passage on the far side of the Sun as an intentional evasion or deliberate concealment often misrepresent the actual orbital mechanics involved. In reality, the trajectory of a body like 3I Atlas follows a hyperbolic path dictated by its initial velocity vector and the gravitational influence of the solar system, not by any conscious navigation or evasive maneuvering. Official positions from space agencies such as NASA and ESA remain conservative, categorizing 3I Atlas as a natural object unless compelling evidence suggests otherwise. This approach reflects standard scientific prudence, assuming conventional explanations until observations provide definitive reasons to reconsider. Throughout the ongoing monitoring process, space agencies continue to observe the object with available assets, carefully avoiding premature or unfounded conclusions about its origins or nature. To distinguish genuine anomalies from observational artifacts or misinterpretations, scientists formulate testable predictions, key tools in separating sound scientific hypotheses from speculative conjecture. If 3I Atlas were truly artificial, it might exhibit sudden, unexpected changes in its trajectory after perihelion that surpass what outgassing physics can account for. Detecting such deviations would involve continued precise astrometric measurements from ground and space-based telescopes, looking for unexplained accelerations or trajectory shifts. Further, alternative observational signatures could include non-cometary thermal emission patterns detectable by infrared space telescopes, or signals such as coherent radio transmissions and polarization characteristics inconsistent with natural dust and gas scattering. While current observational technologies present challenges in detecting these subtle signs, they represent concrete, targeted tests capable of discriminating between natural and artificial origins. However, the geometry of the object's approach introduces additional complexities. As 3I Atlas reaches perihelion on the far side of the Sun from Earth, it becomes temporarily hidden behind solar glare, creating a gap in continuous observation that can last for a month or more. This observational blackout results purely from orbital mechanics, not from any deliberate attempt to conceal, but it nonetheless limits our ability to monitor the object during its most active and dynamically interesting phase. Nevertheless, assets such as the Parker Solar Probe, equipped with its whisper camera, offer a unique vantage point. Positioned closer to the Sun, it could observe the object from perspectives inaccessible to Earth-based telescopes, potentially revealing activity patterns or morphological changes during perihelion that remain hidden from terrestrial observers. Such observations could provide critical insights into the object's behavior and physical state during this crucial phase, filling in gaps left by the limitations imposed by our planet's position in space. The role of the technological hypothesis within scientific discourse is of profound importance, even if it ultimately turns out to be incorrect. Rather than dismissing such ideas outright, this hypothesis functions as a vital alternative lens through which we can interpret perplexing data. It compels scientists to scrutinize existing explanations more thoroughly, pushing the boundaries of conventional understanding. By proposing a different framework, it encourages the pursuit of more precise and targeted observations that can effectively differentiate between competing models. Science, at its core, flourishes through diverse perspectives and the rigorous questioning of assumptions. This diversity fuels progress and prevents stagnation. However, cultivating healthy skepticism demands a delicate balance. It is crucial to distinguish between genuine scientific speculation, testable hypotheses grounded in data, and unfounded conspiracy theories that lack empirical support. The current consideration of a technological origin for the interstellar object known as 3 Atlas exemplifies this distinction. Proponents of this idea do not claim definitive proof. Instead, they present detailed calculations, orbital models, and observable predictions that can be scrutinized through established scientific methods. These efforts serve as a foundation for empirical testing rather than as conclusive evidence. The broader societal fascination with the possibility of extraterrestrial intelligence shapes the cultural context of these discussions. After decades of search for extraterrestrial intelligence, SETI activities, and recent official acknowledgments of unidentified aerial phenomena, public interest in discovering signs of advanced technology in space has surged. Such enthusiasm can act as a powerful motivator for scientific inquiry, inspiring new investigations and hypotheses. Yet it also carries the risk of distorting the interpretation of ambiguous or preliminary data, leading to overinterpretation or premature conclusions. Responsible science communication plays a crucial role here. It requires presenting multiple plausible hypotheses, natural, artificial, or otherwise, while maintaining appropriate levels of confidence and transparency about the current limits of evidence. The possibility of a technological origin for 3 Atlas should be acknowledged as one among several hypotheses, not as the definitive explanation. Presenting it as a serious scientific candidate ensures a balanced approach, preventing undue hype while encouraging continued investigation. Currently, the evidence does not sufficiently favor this hypothesis over more conventional explanations rooted in known cometary physics, which remain plausible despite the object's peculiar properties. The influence of media amplification further complicates this landscape. When scientific speculation is repeatedly reported and shared across social media platforms, it can evolve from tentative hypotheses into seemingly proven facts. Initial scholarly articles which frame the idea as a hypothesis requiring further testing may be transformed through retellings into assertions of probable artificial origin, often omitting the important caveats and nuances. This process underscores the importance of cautious and nuanced communication, especially in the age of information overload. Educationally, these discussions present invaluable opportunities. They exemplify how scientists approach unusual phenomena, generating multiple explanations, designing rigorous tests to distinguish among them, and refining their understanding as new data emerges. The peer review process, a cornerstone of scientific integrity, is essential here. While preliminary findings and conference presentations allow for initial exploration of speculative ideas, robust conclusions depend on thorough evaluation by experts. These peer reviews scrutinize methodologies, statistical analyses, and interpretations to ensure that claims are supported by solid evidence, thereby protecting the integrity of scientific discourse and separating legitimate inquiry from unfounded speculation. Looking ahead, ongoing and future observations will be decisive in testing the validity of the technological hypothesis. Continued astrometric tracking, detailed spectroscopic analysis, and potential spacecraft missions, such as close encounters, will provide critical data. These efforts will help determine whether the peculiarities observed are consistent with natural phenomena, or if they indeed point toward an artificial origin. Until then, maintaining a careful evidence-based approach remains essential, fostering scientific progress while avoiding unwarranted conclusions. If observations of 3I Atlas reveal behavior aligning with the physics of conventional comets, where outgassing produces predictable subtle orbital nudges, then the notion of it being an artificial construct will diminish in plausibility. In such a case, the hypothesis of technological origin will lose ground, giving way to a natural explanation rooted in familiar cometary processes. Conversely, if ongoing and future observations uncover characteristics that are truly anomalous, defying the established understanding of comet behavior, the credibility of the artificial origin hypothesis will grow. This would serve as a strong impetus for scientists to pursue more detailed investigations, probing the object's properties with greater precision and rigor. The crucial tests to distinguish between these scenarios are set to unfold over the next 18 months. During this period, 3I Atlas will complete its passage through the inner solar system, eventually emerging from behind the sun's glare, allowing Earth-based observatories to continue tracking and analyzing it. This extended observational campaign is designed to provide multiple opportunities to evaluate specific predictions associated with both natural cometary origins and potential artificiality. By comparing the collected data against the expected signatures of each scenario, researchers aim to arrive at a clearer understanding of the object's true nature. Regardless of whether the final verdict leans toward a natural or an artificial explanation, the ongoing debate underscores the vital importance of maintaining an open mind while adhering to rigorous, evidence-based standards. Scientific progress relies on the willingness to entertain unconventional possibilities, such as the hypothesis of extraterrestrial technology, while demanding extraordinary proof before accepting extraordinary claims. This balanced approach ensures that extraordinary ideas are given fair consideration, but are subject to the same scrutiny as any other scientific hypothesis. Beyond this, there exists an alternative and equally captivating speculative framework that may be more grounded in current scientific understanding. This is the concept that objects like 3I Atlas could function as seeds for planet formation, an idea that opens new avenues for understanding how planetary systems might originate and evolve. This proposition, known as the planet seeding hypothesis and notably advanced by Suzanne Falsner, offers a compelling perspective on the role of massive interstellar travelers. It posits that such objects captured by young stellar systems might bypass the traditional bottlenecks faced during planet formation. Instead of slowly growing from tiny dust grains through incremental accretion, a process often hindered by physical barriers, these pre-existing sizable interstellar bodies could immediately act as foundational seeds for the rapid development of giant planets. The core challenge in the conventional planet formation paradigm stems from the limited window of time during which giant planets can form. Typically, the protoplanetary disks surrounding young stars, rich in gas and dust, dissipate within about 5 to 10 million years due to processes like photoevaporation and stellar accretion. During this brief period, planetary cores must amass enough mass to trigger runaway gas accretion, transforming into full-fledged giants. Yet this timing constraint introduces a significant problem. How can planetary cores grow quickly enough before the disk's material is lost? A particular obstacle in this process is the so-called meter-size barrier. As planetary embryos grow, they tend to spiral inward and fall into their parent star, primarily because small debris, on the order of meters in size, experiences substantial aerodynamic drag from the surrounding gas. This drag causes their orbits to decay rapidly, preventing them from reaching the critical mass needed for gravitational binding and further growth. The idea of capturing massive interstellar objects provides an elegant solution to this timing dilemma. If young stellar systems can gravitationally snag pre-existing kilometer-scale bodies from the interstellar medium, these seeds could effectively leapfrog over the slow, incremental growth phase. Instead of starting from scratch with tiny dust particles, the system would already possess substantial gravitationally stable building blocks. These captured bodies could then swiftly begin accreting gas and dust from their host disks, accelerating the formation of giant planets. Recent simulations and models presented at the 2025 European Planetary Science Congress and the Division for Planetary Sciences meeting lend support to this capture scenario. They suggest that under certain conditions, particularly in dense young stellar environments, gravitational interactions can indeed facilitate the efficient capture of interstellar objects of significant size. These seeds not only provide a shortcut past the meter-size barrier, but also enable a more rapid and robust formation pathway for giant planets, potentially explaining some of the diversity observed in exoplanetary systems. Recent advancements in astrophysical modeling have shed new light on the process by which massive stars are more adept at capturing interstellar objects compared to their lower mass counterparts. This insight suggests a compelling potential correlation. The more massive a star, the higher its likelihood of ensnaring wandering debris from interstellar space, a mechanism that parallels observed trends in exoplanet demographics, particularly the prevalence of giant planets around larger stars. The core of this mechanism hinges on gravitational focusing effects that occur during close encounters between interstellar visitors, such as the enigmatic object known as 3 Atlas, and nascent stellar systems. Stars with substantial mass create profound gravitational wells, effectively enlarging their capture cross-sections. This means that passing objects are more likely to be drawn into their gravitational influence, increasing the chances of being captured rather than simply passing by. Moreover, these massive stars frequently form within dense stellar clusters, environments characterized by high stellar densities and frequent interactions. During the critical early phases of disk evolution, when circumstellar material is abundant, the encounter rates with interstellar debris are significantly elevated, further amplifying the likelihood of capture. This process of capture and subsequent seeding of planetary building blocks has garnered considerable attention in recent scientific discourse and media coverage. Many now explore how interstellar objects like 3 Atlas could circumvent traditional planet formation barriers, such as the meter-size barrier posed by collisional fragmentation, and instead act as catalysts for rapid planetary growth. These theories posit that such captured bodies serve as initial cores or seeds, accelerating the traditional pathway of core accretion rather than replacing it outright. Instead, capture seeding is viewed as a complementary process that operates alongside conventional mechanisms, especially in environments where dense disks and high encounter rates prevail. Adding further plausibility to this scenario is the chemical evidence gathered by the James Webb Space Telescope, JWST. Observations revealed that 3 Atlas exhibits carbon dioxide-rich outgassing, with abundance ratios indicating its formation in the farthest reaches of its original stellar system, beyond the so-called carbon dioxide snow line, where temperatures plummet below -125 degrees Celsius. Such frigid formation conditions are typical of objects born in the peripheral regions of planetary systems, far from the warmth of their parent stars. When a captured interstellar object, bearing chemical compositions foreign to the host system, merges into a new disk, it could introduce a mixture of volatile compounds and refractory materials from diverse stellar environments, thereby fostering chemical diversity. This process might help explain the observed variety in exoplanet atmospheres and compositions, which often display a surprising heterogeneity. Furthermore, different stellar systems are likely to produce debris with distinct ice compositions and refractory element abundances, depending on their initial formation conditions. When captured, such material from a variety of stellar origins would intermingle within the host disk, enriching it with a mosaic of chemical signatures. As a result, population statistics become vital in assessing the viability of the seeding hypothesis. The upcoming decade's large-scale surveys, such as the Legacy Survey of Space and Time, are expected to uncover numerous interstellar visitors. Should these surveys find that objects like 3 Atlas, if they prove to be exceptionally rare, do not occur frequently enough to supply sufficient material for seeding, the credibility of such scenarios would be challenged due to an apparent scarcity of raw material. Current theoretical frameworks, however, suggest that in the dense, turbulent environments of star-forming regions, The rate at which young stellar systems can capture interstellar objects might be sufficient to influence planetary formation. During the initial few million years, when the circumstellar disks are still massive and actively accreting, these environments are most conducive to permanent capture. This period coincides with the epoch when the primordial disks retain enough gas and dust to support rapid core growth, making the seeding process particularly effective. The concept of capture seeding is not new. It traces back several decades, rooted in the idea that interstellar objects could serve as primordial building blocks for planet formation. Recent theoretical advances, however, have refined this idea, providing more specific predictions regarding the expected rates of capture, the size distributions of captured bodies, and their subsequent evolutionary paths within the host disks. These developments have transformed the hypothesis from speculative to systematically plausible, especially in light of growing observational evidence and sophisticated modeling efforts. Previous research proposed a groundbreaking idea. During the most active phases of planetary system formation, a staggering number, potentially exceeding 10 million of sizable seeds, akin in scale to the asteroid Oumuamua, could be present within a single protoplanetary disk. This paradigm-shifting perspective radically revises the conventional understanding of how planets originate, suggesting that instead of forming solely from the gradual accumulation of smaller particles, planetary systems might frequently incorporate these pre-formed interstellar seeds, which are captured early on and then grow into full-fledged planets. The likelihood of such a capture event, known as capture efficiency, hinges on a multitude of factors. For instance, the relative velocity between interstellar objects passing through a star's neighborhood and the target star system itself plays a crucial role. Slower encounters are more conducive to capture. Additionally, the mass and internal structure of the protoplanetary disk, its density, temperature gradients, and turbulence significantly influence whether a passing interstellar body can be gravitationally tethered. The presence of binary star companions or densely packed stellar clusters can further alter gravitational dynamics, either facilitating or hindering the capture process by modifying the local gravitational landscape. Different stellar environments, such as isolated stars versus dense stellar clusters, are expected to produce diverse signatures in how and when objects are captured. These variations could manifest as distinctive statistical patterns in the properties of planetary systems, effectively serving as fingerprints of their formative environments. Yet, despite the allure of this model, substantial uncertainties persist. Critics underscore the incomplete understanding of the physical mechanics underlying capture, how exactly objects lose enough kinetic energy to become bound, and question the survival prospects of captured seeds. Once trapped, these objects face a perilous journey. They must withstand tidal forces that threaten to rip them apart, avoid ejection from the disk through subsequent gravitational interactions, and then migrate inward or outward to regions where they can efficiently accrete additional material and grow. The evolving structure of the protoplanetary disk adds yet another layer of complexity. These disks are dynamic, rapidly changing environments. Density profiles shift, temperature distributions fluctuate, and turbulent mixing stirs the gas and dust, factors that can either promote the growth of captured seeds or prevent their survival altogether. Fully understanding these processes necessitates advanced, high-fidelity magnetohydrodynamic simulations that integrate the physics of disk evolution with the detailed mechanisms of planetary formation. From an observational standpoint, signatures of this seeding process remain largely in the realm of theory. If planets do form around these interstellar origins, they could carry chemical or isotopic anomalies, distinctive chemical fingerprints that might be detectable in their atmospheres once they are mature. However, current observational capabilities are insufficiently sensitive to easily identify such subtle signatures amidst the cosmic noise. Indirect evidence for the seeding hypothesis could emerge from the statistical properties observed across many exoplanetary systems. If capture events significantly influence planetary outcomes, then the distributions of planet masses, their orbital parameters, and correlations with host star properties should reflect this influence. Some patterns, such as an unexpected abundance of certain orbital configurations or mass ranges, might already be present in existing exoplanet datasets, hinting at the influence of interstellar seeds. It is crucial, however, to distinguish between what our current models reliably predict and what remains speculative. While the physics of gravitational focusing and capture cross-sections are well understood within classical mechanics, the subsequent evolution of these captured objects, particularly the complex chemistry and turbulence within the disk, is still poorly constrained by observations. To clarify the process, visual models and animated simulations can be invaluable. Imagine sequences where interstellar objects plunge into a protoplanetary disk, experiencing drag forces that gradually circularize their orbits and initiate accretion of gas and dust, akin to a cosmic version of a spacecraft entering a planetary atmosphere. This process resembles the traditional core accretion model, but with a vital advantage. The seeds are already sizable and solid, providing a head start in planet formation timelines. Consequently, seeding scenarios could shorten the time required for planetary growth, offering a more efficient pathway compared to the slow, incremental accumulation of smaller particles. Traditional models of planet formation, particularly the core accretion paradigm, outline a lengthy process spanning several million years. Initially, dust grains within a protoplanetary disk collide and stick together, gradually building up kilometer-sized planetesimals, solid building blocks that serve as the foundation for larger planetary bodies. This initial stage, from microscopic dust to sizable planetesimals, demands a significant amount of time. Once these sizable seeds are in place, further accumulation of material occurs, allowing these bodies to grow into full-fledged planets, a process that also unfolds over millions of years. However, recent insights into interstellar objects suggest a potentially revolutionary shortcut. If a planetesimal seed, roughly a kilometer in size, were already captured from interstellar space and introduced into a protoplanetary disk, it could effectively bypass the earliest, most time-consuming phase of formation. Instead of starting from dust, these seeds would begin their growth with a substantial initial mass, significantly shortening the overall timeline required to reach planetary scales. This process, often described as planet seeding, raises intriguing prospects for rapid planet formation, especially in dense stellar environments where such captures might be more frequent. Moving forward, scientists aim to refine this concept through advanced theoretical modeling. Critical to this effort is predicting how often such seeds are captured, capture rates, and assessing how likely they are to survive the tumultuous environment of a young stellar disk. These predictions depend on a complex interplay of factors, including the dynamics within stellar clusters, the distribution of interstellar objects, and the detailed physics governing protoplanetary disk evolution. Combining these elements into comprehensive models presents a formidable challenge, as it involves multiple scales, from the microscopic interactions of dust and gas to the large-scale gravitational influences of entire star clusters. Current computational tools are pushed to their limits by this multifaceted problem, requiring sophisticated simulations that can accurately capture the physics across these diverse scales. While the idea that massive interstellar objects could serve as planetary seeds remains speculative, primarily due to limited observational data, it offers a compelling avenue for testing fundamental theories of planet formation. The peculiar properties of certain interstellar visitors, such as their unexpected sizes or chemical signatures, make them ideal candidates for exploring whether such objects could indeed catalyze planetary growth. Should future observations reveal that such large interstellar bodies are common, the hypothesis of planet seeding would gain substantial credibility. Conversely, if these objects remain exceedingly rare, the traditional models, where planets form gradually from dust within their natal disks, would continue to dominate our understanding. Beyond the immediate context of individual planetary systems, this line of inquiry invites broader questions about how matter exchanged between different stellar systems influences galactic evolution. If interstellar objects can effectively carry chemical and physical information across vast distances, they could serve as messengers, facilitating a form of cosmic communication that shapes the composition and development of planetary systems over billions of years. This perspective challenges the notion of planetary uniqueness, suggesting instead that shared processes and exchange of material might be fundamental drivers of galactic evolution. Understanding these connections demands an interdisciplinary approach, bridging observational astronomy, which detects and characterizes these objects, with theoretical astrophysics and planetary science, which seeks to interpret their significance within the broader cosmic context. Such integration pushes traditional scientific boundaries, requiring new frameworks and collaborative efforts to unravel the complex web of processes at play. Amid these scientific pursuits, the timing of recent discoveries presents its own intriguing puzzle, what we might call the cosmic timing puzzle. The recent detection of such a massive interstellar object, made possible by a confluence of technological advancements, observational strategies, and cosmic coincidences, is remarkable. It prompts us to ask, why are we observing these colossal interstellar visitors precisely now? In the past few years, the observational infrastructure supporting these discoveries has undergone a rapid transformation. The deployment of sophisticated wide-field survey telescopes, such as those in the southern hemisphere, has vastly increased our capacity to scan the skies for transient objects. For example, the Atlas South Observatory, operational since 2022, complements earlier observatories in Hawaii, creating a global network capable of continuous around-the-clock monitoring of the night sky. This interconnected system enables astronomers to track transient phenomena, like interstellar visitors, in real time, capturing fleeting moments that would have been impossible to observe just a few years ago. The specific geometric advantages of the current observational setup played a crucial role in the detection of the interstellar object in question. Its trajectory, aligned favorably with the survey coverage areas, allowed for timely discovery and detailed follow-up observations. As Earth's rotation and the positioning of observatories shifted, different sites gained optimal viewing conditions, ensuring continuous monitoring and increasing the likelihood of detection. This convergence of technological capability, strategic observational planning, and natural cosmic alignment illustrates how a series of fortunate circumstances can culminate in groundbreaking discoveries. Whether this is a mere statistical fluctuation, an unusual but expected result within the vastness of space, or a sign of an underlying physical phenomenon, remains an open question. The recent advances in astronomical infrastructure, coupled with the rapid evolution of astronomical response systems, has marked a significant breakthrough in how we study transient celestial objects. Advanced pipelines now enable near-instantaneous coordination, linking initial discovery telescopes with a network of follow-up instruments, dramatically reducing reaction times from weeks to mere hours. This efficiency was exemplified when, on July 1, 2025, the Chilean observatory responsible for spotting the interstellar object designated 3I Atlas promptly flagged it as potentially noteworthy within just a few days. Following this, the Hubble Space Telescope swiftly scheduled observations, which were conducted within 3 weeks of the initial detection. Not long after, the James Webb Space Telescope, JWST, carried out spectroscopic analysis just over a month post-discovery. This level of synchronized, fast-paced collaboration signals a quantum leap in our capacity for astronomical responsiveness, transforming reactive science into a proactive, real-time pursuit. The geometry of 3I Atlas's approach played a pivotal role in enabling this rapid follow-up. Its trajectory was nearly aligned with the ecliptic plane, the flat, disk-like region in which most solar system objects orbit the Sun, making it highly accessible to the majority of survey telescopes that concentrate their efforts along this plane. Such an alignment significantly simplified subsequent observations because it kept the object within the operational parameters of multiple ground and space-based facilities, ensuring consistent tracking and detailed examination. In contrast, objects with highly inclined or retrograde orbits, those moving in the opposite direction or at steep angles relative to the ecliptic, would naturally have been more challenging to detect and characterize, potentially skewing our current sample toward ecliptic-aligned visitors like 3I Atlas. This observational bias emphasizes that our understanding of interstellar objects might be shaped heavily by their orbital geometry, with the most easily observed bodies not necessarily representing the full diversity of the population. The intense media coverage surrounding the initial mass estimates of 3I Atlas demonstrates how sensational framing, particularly when emphasizing extreme or anomalous characteristics, can amplify public and scientific interest. Early calculations, which suggested a mass based on non-gravitational acceleration limits, attracted widespread attention and speculation. However, these estimates depend heavily on assumptions about the physics of outgassing, the release of gas from the object's surface, which remain subjects of ongoing peer review and refinement. Consequently, the public and scientific communities should exercise caution in interpreting preliminary findings, recognizing that initial reports are subject to change as analysis becomes more rigorous and data is scrutinized. The ongoing investigation into the mass, chemical composition, and population characteristics of 3I Atlas remains an active research frontier rather than a settled story. Responsible scientific communication must clearly distinguish between early, tentative results and well-established conclusions to avoid misrepresenting the state of knowledge. Maintaining appropriate excitement while emphasizing the provisional nature of initial findings is vital for fostering public trust and scientific integrity. Moreover, opportunities provided by space-based vantage points add a crucial dimension to our understanding that terrestrial observatories cannot match. The Parker Solar Probe, equipped with its Whisper camera, is expected to observe 3I Atlas during its perihelion passage, scheduled between late September and early November 2025, offering a unique solar-side perspective that ground-based telescopes are unable to achieve due to the object's close proximity to the Sun in the sky. These space-based observations could reveal activity patterns or morphological changes, such as surface features, outgassing behavior, or tail formation, that remain hidden from Earth-bound instruments. Since the viewing geometry differs from that of Earth, these data could help resolve lingering questions about unusual phenomena observed groundside, like the object's sunward glow or its evolving tail structure. Understanding the behavior of 3I Atlas near perihelion, its closest approach to the Sun, relies critically on data collected from multiple vantage points. The variation in observed features driven by differing viewing angles offers a powerful explanation for some of the apparent statistical anomalies and morphological peculiarities. These sample size effects, stemming from the limited number of observations and perspectives, highlight that the full complexity of such interstellar objects can only be appreciated through diverse, multifaceted data collection. In essence, the more vantage points and observations we gather, the clearer our picture becomes, reducing the likelihood that perceived anomalies are merely artifacts of limited perspective. Interstellar travelers, Objects originating beyond our solar system are exceedingly rare, and with only 3 confirmed examples to date, Oumuamua, Borisov, and the latest 3I Atlas, drawing broad conclusions about the overall population remains fundamentally uncertain. Relying solely on such a tiny sample makes any demographic inference virtually meaningless because the data can be heavily skewed by early fluctuations or chance occurrences. Often, what appears to be an anomaly or an outlier simply reflects the statistical noise of small numbers, which tends to smooth out as more data is accumulated and sample sizes grow larger over time. An alternative perspective, however, suggests that the remarkable size of 3I Atlas might genuinely place it in the extreme tail of the interstellar object distribution, an extraordinary statistical unicorn that happened to appear during humanity's very first systematic surveys. Although such an event may seem improbable, it is entirely consistent with the nature of statistical distributions. Outliers, especially those residing in the far fringes, are by definition rare but inevitable in large populations. Their sudden appearance, while startling, is a natural consequence of the tail behavior of probability distributions, and their rarity only makes them more memorable when they finally manifest. The rapid advancements in observational technologies across multiple domains have dramatically enhanced our ability to detect and track faint, distant objects. Ground-based telescopes equipped with adaptive optics systems now significantly reduce atmospheric distortion, allowing for sharper images and more precise measurements. Space-based telescopes eliminate the blurring effects of Earth's atmosphere altogether, opening a clearer window to the universe. Meanwhile, improvements in detector technologies such as increased quantum efficiency and reduced electronic noise have further pushed the boundaries of what can be observed and measured with accuracy. These technological strides have shifted the horizon of detectability, enabling astronomers to see objects that were previously simply invisible or indistinguishable from background noise. As a result, what might once have been overlooked or remained hidden in the depths of space is now within our grasp. This shift means that an apparent sudden influx of massive interstellar visitors could in fact reflect our enhanced ability to detect objects that have always been out there, just beyond the reach of earlier surveys. The evolution of survey strategies has also played a crucial role. Modern programs now optimize their approaches through improved cadences, how frequently the sky is revisited, and by refining data processing algorithms that sift through enormous volumes of information more efficiently. Enhanced coordination among various observational facilities, ground-based telescopes, space telescopes, and specialized survey instruments ensures comprehensive sky coverage and rapid follow-up capabilities. These improvements work synergistically to maximize detection rates across a broad spectrum of transient phenomena, including interstellar objects. The Vera Rubin Observatory epitomizes these advancements, representing the culmination of technological and strategic progress. Once fully operational, its Large Synoptic Survey Telescope, LSST, will systematically scan the entire southern sky every few nights over a decade-long campaign. This persistent high-cadence monitoring is expected to detect hundreds, perhaps even thousands, of interstellar objects passing through our solar system. Such a wealth of data will transform the current picture, based largely on anecdotal or sparse observations, into a robust, statistically meaningful understanding of the true demographics, size distributions, and origins of these celestial visitors. This surge in observational capability has profound practical implications beyond mere academic curiosity. Recognizing that massive interstellar objects might be more common than previously thought necessitates the development of rapid response protocols for future discoveries, so we can swiftly gather detailed data or even plan dedicated missions. The infrastructure and methodologies refined during the characterization of 3I Atlas serve as valuable templates for orchestrating such future campaigns, ensuring that we are better prepared to study these objects comprehensively and efficiently. Looking ahead, the next 12 to 18 months will constitute the most data-rich window ever available to observe an interstellar visitor. Multiple space-based and ground-based facilities will work in concert to track 3I Atlas throughout its entire passage around the Sun. This unprecedented temporal coverage will allow scientists to monitor its activity, morphological evolution, and chemical changes as it responds to increasing solar heating. Such detailed, continuous observations will deepen our understanding of the physical and chemical processes at play, ultimately shedding light on the nature and origins of these enigmatic wanderers from beyond our star system. Effective communication strategies for ongoing observations must carefully balance the inherent uncertainties of scientific research with the public's fascination with potentially groundbreaking discoveries. The scientific process itself is inherently iterative, involving the formulation of hypotheses, rigorous testing, and subsequent refinement, timeframes that often do not align with the rapid cycles of media coverage or the public's desire for conclusive answers. To navigate this landscape responsibly, the scientific community relies on robust quality control mechanisms such as peer review, independent replication, and thorough analyses by multiple teams. These steps serve to distinguish genuine discoveries from artifacts introduced by instruments or errors in data interpretation. Initial estimates of the mass and physical characteristics of the interstellar object known as 3I Atlas will be subjected to intense scrutiny and rigorous evaluation. Researchers will examine the methodologies employed, scrutinize the underlying assumptions, and consider alternative interpretations. This process is not new. Throughout history, many objects initially deemed anomalous or unprecedented have eventually been explained through improved observations and more sophisticated models. Such anomalies often serve as catalysts for scientific progress, prompting refinements that lead to a clearer understanding of the phenomena involved. The scientific method's strength lies precisely in this capacity for self-correction, ensuring that conclusions evolve as data quality and theoretical frameworks improve. The timing of this discovery likely reflects the natural evolution of technological capabilities in astronomy. Past generations of surveys lacked the sensitivity, sky coverage, and follow-up observation tools necessary to detect and thoroughly study interstellar visitors like 3I Atlas. As observational technology advances, so does our ability to recognize and analyze such objects systematically. Watching science operate in real time amidst these puzzles offers significant educational value, illustrating how hypothesis testing, statistical analysis, and awareness of observational biases intertwine to drive discovery. 3I Atlas in particular provides an exemplary case study for understanding these core scientific processes. From a broader cosmic perspective, interstellar visitors are more than isolated curiosities. They carry vital information about processes that operate at galactic scales over billions of years. Whether 3I Atlas turns out to be a typical or an extraordinary example, it represents a sample from the vast and diverse population of debris moving between stellar systems. These objects offer glimpses into environments and evolutionary processes that are otherwise inaccessible to direct study, acting as messengers from distant star systems and ancient galactic history. Looking ahead, upcoming survey capabilities promise to resolve many of the current timing puzzles by enabling statistical analysis of large samples of such objects, rather than relying on individual case studies or speculation. The shift from anecdotal observations to comprehensive population studies is expected to occur within the next decade, facilitated by the deployment of next-generation telescopes and survey systems that will dramatically increase detection rates. The apparent coincidence between our technological readiness and the recent discovery of a massive interstellar visitor may in fact be a sign of deeper thresholds being crossed, either revealing previously hidden aspects of the interstellar medium, or simply reflecting the natural progression of observational capabilities. In either scenario, 3i Atlas has opened a crucial observational window that is poised to shape the future of interstellar object astronomy. Its study exemplifies how technological advancement and scientific inquiry can work hand in hand, providing insights that will inform research for years to come. This discovery underscores the importance of patience, rigor, and transparency in science, ensuring that our interpretations evolve in step with our growing ability to see deeper into the cosmos. The innovative techniques, carefully designed protocols, and pressing scientific questions that are emerging from the study of interstellar visitors like this will fundamentally influence how future discoveries are made, understood, and contextualized. They will shape our approach to unraveling the complex implications these objects hold for our comprehension of our position within the vast galactic ecosystem. Among the most exhilarating opportunities this research opens up is the prospect of observing the interstellar object, known as 3i Atlas, from an entirely new vantage point as it nears the planet Mars. This significant event, often referred to as the Mars encounter, is set to occur as the interstellar visitor comes within roughly 30 million kilometers of Mars on October 3, 2025. Such an approach creates an unparalleled chance for multi-vantage point observations, allowing scientists to study the object from different perspectives and gather data that could reveal previously hidden details about its composition, structure, and activity. The proximity, about 0.2 astronomical units, means that the object will be well within the operational range of several Mars-orbiting spacecraft, potentially enabling the first close-up observations of an interstellar comet from assets positioned beyond Earth's immediate vicinity. Currently, the European Space Agency operates multiple missions around Mars, including the venerable Mars Express, which was launched back in 2003 and has been functioning successfully for more than 2 decades. Alongside it is the Trace Gas Orbiter, which arrived in 2016 as part of the ExoMars program. Both spacecraft are equipped with advanced imaging systems and scientific instruments capable of observing and collecting data on interstellar objects during their flybys or passes nearby. However, due to operational constraints, power limitations, and the need for precise mission planning, any observations of 3i Atlas would require careful coordination and timing. Further, NASA's Mars Atmosphere and Volatile Evolution (MAVEN) orbiter, which has been studying Martian atmospheric escape processes since 2014, could also contribute to the observation campaign. Although MAVEN was primarily designed for atmospheric research rather than deep space observations, its instruments might be repurposed or adapted to gather valuable data during the encounter, provided mission managers can accommodate the necessary pointing and data collection priorities. Another potential asset is the Mars Reconnaissance Orbiter, which has been operational since 2006. Renowned for its high-resolution imaging capabilities, it primarily focuses on surface features but could, in principle, attempt to observe 3i Atlas at its closest approach. Nonetheless, even at this proximity, the object will remain tens of millions of kilometers away, far beyond the resolution limits of high-rise imaging, which are optimized for detailed surface features rather than distant celestial objects. Despite these limitations, any observations from Mars orbit would be invaluable for constraining the object's brightness profile, phase angle effects, and coma asymmetry, parameters that are difficult or impossible to measure from Earth-based telescopes during the same period. Importantly, observing 3i Atlas from Mars presents a different viewing geometry compared to Earth-based observations. This alternative perspective could provide unique insights into the distribution and behavior of dust particles, scattering phenomena, and gas emissions, revealing details that might be obscured or ambiguous when viewed from our planet. For instance, the way dust and gas are distributed around the nucleus and how they scatter sunlight could appear quite different from Mars's vantage point, offering a richer, more nuanced understanding of the object's activity. Beyond imaging, the scientific value of the Mars encounter extends into the realm of photometric measurements, precise assessments of brightness variations over time. These data could be instrumental in gauging the activity levels of 3I Atlas, testing and refining theoretical models that link observed outgassing activity to the object's mass estimates. Moreover, independent brightness measurements from Mars's perspective would serve as a vital complement to Earth-based data, helping to resolve any discrepancies or ambiguities about the comet's activity and physical properties. In sum, the upcoming Mars flyby offers a rare and invaluable opportunity to expand our understanding of interstellar objects. The different observational vantage points, combined with the capabilities of current spacecraft, promise to deepen our insights into the nature and behavior of 3I Atlas, ultimately advancing our broader quest to comprehend the diverse and dynamic population of objects that traverse the space between stars. Effective coordination between Mars-based assets and ground-based telescopes hinges on meticulous timing and robust communication protocols, all aimed at achieving synchronized observations whenever feasible. This synchronization is vital for maximizing the scientific yield from the encounter, especially when tracking an object as elusive and dynamic as interstellar visitor 3 Atlas. One of the primary complications in this endeavor is the finite speed of light, which introduces a delay, roughly 16 minutes, between the moment a signal is sent from Earth and when it is received by Mars orbiters during the critical observation window. This inherent lag renders real-time control and immediate response impractical, necessitating the careful design of pre-planned observation sequences. These sequences are crafted to ensure that multiple assets, both from Earth and Mars, operate in harmony, capturing complementary data that, when combined, enrich our understanding of the object's behavior and properties. Communication strategies are equally crucial. They must be tailored to optimize data transmission within the constraints imposed by the relative positions of Earth and Mars, which change over time. The data rates achievable by Mars orbiters depend heavily on their orbital geometry and the relative alignment of Earth and Mars. During the encounter period, however, the geometry tends to be favorable, providing window periods when the distance and alignment allow for more efficient data transfer. These windows enable the rapid relay of observations back to Earth, ensuring that the information can be integrated promptly with data from terrestrial telescopes for a comprehensive analysis. The timeline of the encounter extends across several days centered around October the 3rd, which marks the closest approach of 3 Atlas to the Sun. During this interval, multiple observation opportunities are available as the interstellar object traverses the Martian sky, offering different vantage points and background conditions. Since each spacecraft involved, whether orbiting Mars or on Earth, has unique orbital periods and pointing capabilities, their windows of optimal observation do not perfectly overlap. This variability requires careful scheduling to ensure that each asset captures the most informative data at the right moments. Brightness predictions derived primarily from Earth-based observations and models suggest that 3 Atlas should remain detectable by the sensitive instruments on board Mars orbiters throughout the encounter. Nevertheless, the actual visibility will depend on several factors. These include the development and extent of the object's coma, the cloud of gas and dust surrounding its nucleus, as well as the dust production rates and the intrinsic brightness of its nucleus itself. As the object approaches perihelion and continues to warm, its activity levels and brightness are expected to change, influencing detectability. Therefore, while models provide valuable planning estimates, The actual success of observations hinges on real-time behavior, which remains uncertain until the object's activity is observed directly. From a geometric perspective, Mars-based observations hold a significant advantage during this period. While from Earth's vantage point, 3 Atlas appears increasingly close to the Sun in the sky as it nears perihelion, posing observational challenges due to solar glare and atmospheric scattering. Mars orbiters do not face these limitations. Their different vantage point in space allows them to observe the object without the interference of Earth's atmosphere and with a clearer line of sight, thus providing more consistent data. The safety considerations for these Mars missions are minimal. The encounter distance, approximately 30 million kilometers, is vast relative to the scale of the solar system, equating to roughly 75 times the distance between Earth and the Moon. This distance is comfortably outside any collision risk zone, and operational hazards to Mars orbiters are negligible. Consequently, the observation window presents an essentially zero-risk scenario, making it an ideal opportunity for scientific investigation. Historical precedents bolster confidence in such observations. Mars orbiters have previously glimpsed asteroids, comets, and other solar system objects under favorable geometric conditions. Although none of these past observations involved interstellar objects exhibiting the unusual characteristics of 3 Atlas, the technical challenges remain similar. Precise spacecraft pointing is essential, requiring high accuracy to lock onto a distant moving target. Instruments must be carefully calibrated to ensure data quality, especially when observing targets that differ unexpectedly from typical solar system bodies. Additionally, data processing pipelines, originally designed for analyzing Mars's surface features and atmospheric phenomena, must be adapted to handle the specific demands of distant point source observations, such as tracking the faint glow of a comet nucleus against the background of space. In summary, while the coordination of Mars assets and ground-based telescopes during the 3 Atlas encounter involves complex logistical and technical considerations, it is a feasible and promising venture. The combination of favorable geometry, minimal mission risk, and past operational experience positions this multi-vantage observational effort as a potentially groundbreaking step toward unraveling the mysteries of this extraordinary interstellar visitor. Mission teams face the challenge of tailoring their existing operational protocols to effectively observe targets that differ markedly from their primary scientific goals. This adaptation is crucial, especially when dealing with transient and unpredictable objects like interstellar visitors. To maximize the scientific return from the upcoming Mars encounter with 3I Atlas, a meticulous approach to data integration is essential. Measurements obtained from Mars-based instruments and those from Earth must be carefully cross-calibrated, requiring sophisticated geometric modeling to reconcile differences in vantage points. Such precision ensures that the data collected from these distinct perspectives can be meaningfully compared, ultimately providing a cohesive picture of the object's behavior. A key aspect of this process involves accounting for the various viewing geometries, as well as the differences in filter systems and detector characteristics between spacecraft and ground-based observatories. Each instrument's unique response to light, spectrum, and spatial resolution must be calibrated appropriately, so that combined analyses are accurate and scientifically robust. Given the inherent limitations imposed by distance, especially the vast separation between Mars and Earth, expectations regarding the level of detail achievable must be realistic. The observations from Mars are unlikely to yield high-resolution images of the nucleus or the fine structure of the coma. Instead, they will likely provide valuable photometric data, measurements of brightness variations, and perhaps low-resolution morphological information that can reveal general features or activity patterns. Despite these limitations, even limited data sets are immensely valuable. They expand our observational archive and can offer crucial insights into the behavior of interstellar objects during close planetary approaches. This campaign is more than a one-off event. It serves as a pioneering example of future multi-asset coordination. As interplanetary missions proliferate and technological capabilities advance, the routine deployment of coordinated observations, leveraging multiple spacecraft, telescopes, and vantage points, will become standard practice for studying transient phenomena across the solar system. Such synergy will significantly enhance our understanding of asteroids, comets, and other visitors from interstellar space. Effective communication with the public about these observations requires a delicate balance. While it is important to manage expectations, especially regarding the inability to produce high-resolution imagery comparable to popular science illustrations, it is equally vital to highlight the scientific value of the multi-vantage photometric and astrometric data being collected. These measurements taken from different points around the solar system can reveal subtle details about the object's activity, rotation, and trajectory, providing insights that are otherwise impossible to obtain. Furthermore, the Mars encounter marks just the beginning of an extended observational campaign. As 3i Atlas continues its journey inward, the data gathered from Mars will set the stage for even more detailed and exciting observations during subsequent close approaches to other planetary systems. Planning for these future efforts must carefully consider the operational constraints of each participating spacecraft, including spacecraft health, power availability, communication schedules, and the overarching priorities of each mission. Agencies from Europe and America will coordinate their efforts, making strategic decisions based on the feasibility of observation, resource allocation, and mission safety. Irrespective of the specific involvement of each Mars spacecraft, the encounter represents a rare and invaluable opportunity in interstellar object astronomy. The simultaneous multi-perspective observations from different assets across the solar system will deepen our understanding of these enigmatic travelers. The rich dataset, combining continuous Earth-based monitoring with Mars-based observations, will provide unprecedented temporal and geometric coverage. This comprehensive approach will allow scientists to track how the object responds to the increasing solar heating as it approaches perihelion, unveiling the dynamic evolution of its activity and physical properties in ways never before possible. As the cosmic journey of 3i Atlas continues, anticipation builds toward an even more extraordinary chapter as it prepares for its next significant gravitational encounter near Jupiter. This event, often referred to as Part 12, the Jupiter opportunity, represents a rare and invaluable window for scientific investigation, offering the potential for insights that could redefine our understanding of interstellar objects and their interactions with planetary environments. On March 16, 2026, gravitational forces will orchestrate a celestial dance, bringing 3i Atlas to within 53.6 million kilometers of the mighty gas giant. To put that distance into perspective, it is roughly equivalent to about 0.358 astronomical units, the average distance from Earth to the Sun, placing the interstellar visitor squarely within reach of NASA's Juno spacecraft, which is already engaged in an extended mission orbiting Jupiter. This proximity presents perhaps the most promising chance in the entire passage of this enigmatic object through our solar system for a close-up, in situ study. Over recent years, numerous scientific teams have laid the groundwork for ambitious mission concepts aimed at capitalizing on this fleeting opportunity. These proposals, crafted by researchers including Loeb, Hibbard, Crow, and others, outline complex yet potentially achievable strategies to redirect Juno's trajectory toward an intercept with 3i Atlas. The core idea hinges on utilizing gravitational assist maneuvers, slingshot techniques that leverage Jupiter's immense gravitational pull to alter the spacecraft's path, combined with the residual fuel on board. While the technical challenges are significant, advancements in orbital mechanics and propulsion make such a rendezvous plausible. Achieving this would require precise execution of what aerospace engineers call an Oberth effect maneuver. This involves firing Juno's thrusters at the closest approach point to Jupiter, where the spacecraft's velocity is at its peak, maximizing the efficiency of propellant use. In essence, each burst of engine thrust at this juncture amplifies the spacecraft's momentum, allowing it to fine-tune its trajectory and intercept the interstellar visitor with remarkable accuracy. The maneuver is a testament to the ingenuity of orbital physics, transforming Jupiter's gravitational well into a tool for unprecedented exploration. The idea of redirecting Juno for such a mission has garnered attention beyond the scientific community, reaching the halls of Congress. Official inquiries and letters from representatives have called for detailed analyses of the feasibility and potential benefits of repurposing Juno's mission parameters. This political recognition underscores the extraordinary public fascination with 3I Atlas and highlights the broader significance of such an encounter. An opportunity that, given the rarity of interstellar visitors, might not present itself again for decades or even longer. The potential scientific gains from a successful in situ sampling are staggering. Unlike remote observations from Earth-based telescopes or even orbiters designed primarily for planetary science, a direct encounter with 3I Atlas could yield definitive data on its composition, structure, and physical properties. Instruments on board Juno could analyze dust particles directly, measuring grain size distributions, isotopic ratios, and magnetic characteristics with a precision unattainable from afar. Such measurements could confirm or challenge spectroscopic inferences, providing concrete evidence about the chemical anomalies observed, such as the nickel-to-iron ratio puzzle, the unusually high carbon dioxide content in its ice, and other enigmatic features. In essence, a close mission would serve as a scientific gold standard, resolving long-standing questions about the true nature of this interstellar visitor and its origins. It would move beyond conjecture and spectroscopy to tangible physical evidence, a feat that could unlock secrets about the building blocks of planetary systems, the processes of matter ejection, and the diversity of objects traversing interstellar space. However, such an endeavor does not come without risks and trade-offs. A comprehensive risk-benefit analysis must weigh the potential scientific rewards against the technical challenges and resource commitments. Repurposing Juno's primary mission objectives, focused on mapping Jupiter's gravity, magnetic fields, and atmospheric dynamics, would require diverting its operations toward a highly specialized one-time encounter. This involves considerations of fuel reserves, spacecraft health, and mission longevity. Ultimately, the decision to pursue this bold trajectory hinges on whether the scientific community and policymakers deem the potential breakthroughs worth the investment and operational risks. If successful, the in situ analysis during the Jupiter encounter could mark a historic milestone, perhaps the first time humanity has directly sampled an interstellar object in the vicinity of a giant planet, and open new frontiers in planetary science and interstellar exploration. Extending Juno's mission to focus on the intricate mapping of Jupiter's gravitational nuances, magnetic field intricacies, and atmospheric dynamics represents a pinnacle of planetary exploration. However, redirecting this spacecraft to pursue the interstellar visitor known as 3I Atlas would inevitably come at the expense of these ongoing investigations. The primary obstacle to such a maneuver lies in the limited fuel reserves that Juno was not originally designed to utilize for significant trajectory modifications. Its propulsion system is optimized for orbital maintenance and minor adjustments around Jupiter, not for major course changes. Achieving a rendezvous with 3I Atlas would demand the expenditure of nearly all remaining propellant, effectively ending any prospects of resuming or continuing Jupiter-focused science operations. Before any such decision is made, comprehensive engineering assessments are essential to determine whether Juno's propulsion capabilities can generate the necessary velocity change, known as delta V, to intercept the interstellar object within the existing fuel constraints. These calculations involve complex orbital mechanics that take into account Jupiter's intense gravitational influence, the current trajectory of Juno, and the predicted path of 3I Atlas as it traverses the outer solar system. The challenge is substantial. Precise navigation and fuel modeling are required to ensure that the spacecraft can align its course accurately without jeopardizing its integrity or mission objectives. Given these hurdles, alternative observation strategies leveraging other assets may provide valuable scientific insights without necessitating a full mission redirection. For instance, the European Space Agency's JUICE mission, currently en route to the Jovian system, might be capable of performing distant observations, depending on its arrival timing and orbital configuration relative to 3I Atlas. Similarly, NASA's Psyche spacecraft, which is headed toward the asteroid belt, could potentially contribute to the observational campaign if its trajectory aligns favorably. Meanwhile, ground-based telescopes will continue their critical role throughout the Jupiter encounter window, offering complementary data streams that enhance understanding of the interstellar visitor. Facilities like the James Webb Space Telescope, the Hubble Space Telescope, and large terrestrial observatories are prepared to maintain extensive monitoring campaigns regardless of spacecraft involvement. Moreover, the SphereX Space Telescope, designed for all-sky infrared surveys, is uniquely suited to contribute detailed observations of 3I Atlas's extended carbon dioxide coma during its passage near Jupiter. Its wide field of view and infrared sensitivity enable it to track large-scale changes in the coma's morphology, as the object warms while approaching perihelion, providing invaluable data on its activity and composition. Beyond the scientific and technical considerations, there are broader policy implications tied to this decision. The potential to redirect Juno's mission extends beyond pure scientific curiosity. It touches on planetary defense preparedness, interstellar visitor response protocols, and the necessity of international coordination in studying significant astronomical phenomena. The precedent set by 3I Atlas's investigation will likely influence future strategies for rapid response to such interstellar objects, shaping how agencies allocate resources and plan collaborative efforts. Cost-benefit analyses are crucial in weighing the guaranteed loss of primary Juno science objectives against the uncertain but potentially transformative gains from close-up interstellar exploration. These decisions involve not only technical feasibility but also the prioritization of scientific objectives, balancing the value of detailed planetary data against the high scientific returns of studying a rare interstellar visitor. The geometry of the encounter during Jupiter's orbit presents both advantages and disadvantages compared to other observation windows, influencing the timing, quality, and scope of possible data collection. In sum, while redirecting Juno to intercept 3I Atlas offers tantalizing scientific possibilities, it must be carefully balanced against the mission's original goals, technical constraints, and broader strategic considerations. The choice will shape the future of interstellar object study, highlighting the complex interplay between exploration, policy, and scientific opportunity. The outer reaches of our solar system provide a vantage point ideally suited for observation, largely free from the disruptive influence of the sun's glare and radiation. This environment allows telescopes and spacecraft to monitor interstellar objects with minimal interference, offering clearer insights into their nature. However, the vast distances involved come with significant challenges, particularly in maintaining real-time communication. The enormous space separating us from these distant visitors diminishes their apparent brightness from Earth, making detailed observation more difficult for ground-based telescopes. Furthermore, the timeline for space missions is critically tight. Planning, analyzing, and executing trajectory modifications, a necessary step if we decide to redirect a spacecraft like Juno, requires months of meticulous preparation. Any delay in decision-making could jeopardize the opportunity to make meaningful observations during the fleeting window, when the object is optimally positioned for close-up study. If NASA opts to attempt a course correction to Juno's trajectory to intercept or approach 3I Atlas, preparations must begin well in advance. This involves not only technical adjustments, but also comprehensive analyses of orbital mechanics, fuel requirements, and mission safety protocols. International collaboration presents a promising avenue to maximize scientific return. Coordinated efforts with European and Japanese space agencies could enhance observational coverage and data sharing, especially during the encounter period. Sharing data sets and jointly analyzing samples or measurements obtained during the flyby could lead to breakthroughs in understanding the object's composition, physical properties, and behavior in the Jovian environment. The global fascination with 3I Atlas underscores the importance of international cooperation, both scientifically and politically. Such partnerships amplify the scope of research and foster diplomatic goodwill, while also providing educational opportunities to inform the public about the complex decision-making processes involved in space exploration. These processes involve balancing competing scientific priorities, assessing technical and operational risks, and making resource allocation decisions amid uncertainties. An intricate dance that reflects the realities of contemporary space missions. Historical precedents demonstrate that mission flexibility can unlock unforeseen scientific opportunities. For example, the Deep Impact mission successfully conducted a flyby of Comet Hartley 2, despite originally being planned for a different target. Similarly, various spacecraft initially aimed at asteroid belts or other objectives have been redirected to pursue unexpected opportunities, often yielding valuable data and insights. These experiences highlight the importance of adaptable mission planning, where the ability to pivot can significantly enhance scientific returns. Achieving a successful Juno redirection requires precise navigation solutions, robust thermal management for the extended cruise phase, recalibration of onboard instruments tailored to the new target's characteristics, and modifications to communication protocols to support operations at greater distances from Earth. Juno's onboard instruments, such as magnetometers, gravity sensors, microwave radiometers, infrared imagers, and charged particle detectors, offer the potential to gather unparalleled insights into 3I Atlas's size, composition, and interaction with the solar wind environment. However, the communication delay inherent in Jupiter's distance must be factored into mission planning. Data transmission rates are limited, and the spacecraft's systems are operating closer to or beyond their originally intended lifespan. Consequently, any encounter with 3I Atlas may represent Juno's final major scientific contribution before the mission concludes. In the upcoming months, NASA will carefully evaluate whether a mission redirection is technically feasible, scientifically justified, and resource efficient. This decision-making process will dictate whether we seize the opportunity to study this enigmatic interstellar visitor up close or rely solely on remote observations. Regardless of the outcome, the encounter has already demonstrated the extraordinary scientific interest sparked by 3I Atlas's anomalous characteristics, emphasizing the importance of flexibility, preparedness, and international cooperation in exploring the frontiers of our solar system. Whether through a direct spacecraft encounter or by leveraging continued remote sensing observations, the upcoming Jupiter phase of 3I Atlas's voyage promises to serve as a critical testing ground for the theoretical models that aim to decode its extraordinary nature. These investigations will scrutinize the assumptions underpinning our understanding of interstellar objects, providing invaluable data that could either reinforce or challenge existing frameworks. Yet, irrespective of how the observational data unfold, the scientific community must prepare to respond adaptively to the insights gleaned from these unprecedented campaigns, an endeavor that will undoubtedly shape the trajectory of astrophysical research for years ahead. In this context, the implications of 3I Atlas extend far beyond the immediate goal of characterizing a lone interstellar visitor. Instead, they reach into the core of fundamental questions about the nature of debris populations dispersed across vast galactic domains, the intricate processes governing planetary system formation, and the chemical pathways that have sculpted matter over cosmic epochs. Whether the initial estimates of the object's mass and size, such as a 5-kilometer nucleus weighing in at over 33 billion tons, stand the test of further scrutiny or require significant revision, the very existence of this object compels astronomers to confront critical gaps in their theoretical understanding. These gaps, in turn, will direct research efforts, inspire new models, and foster innovative hypotheses that can better explain how such colossal fragments are ejected from planetary systems and survive the arduous journey through interstellar space. Current models of ejection mechanisms face formidable challenges in accommodating objects of this magnitude. The prevailing understanding suggests that ejecting a body of such size and mass with high efficiency is difficult. The physical processes involved, such as gravitational interactions, tidal forces, and collision cascades, appear insufficiently robust or efficient to produce such large debris without destruction. This discrepancy hints at two possibilities. Either our theoretical frameworks require substantial updating to incorporate previously unconsidered processes, or 3I Atlas is an outlier of extraordinary statistical rarity. If future analyses confirm that the object's nucleus truly spans around 5 kilometers and carries a mass in the realm of billions of tons, then the models of planetary debris ejection will need significant revision. The challenge will be to elucidate mechanisms, possibly involving rare stellar flybys, unique planetary scattering events, or yet unknown processes that can propel such massive objects into interstellar space without fragmenting or dissipating their integrity. Stellar flyby scenarios, for instance, might warrant re-evaluation, especially in the context of their ability to eject large, intact bodies. Similarly, models of planet-to-planet scattering, which typically account for smaller debris, may need to be examined under the lens of less common but more energetic or geometrically favorable configurations that could facilitate the ejection of kilometer-scale objects without catastrophic fragmentation. These considerations could fundamentally alter our understanding of debris dynamics, planetary system evolution, and the statistical likelihood of encountering such massive interstellar visitors. Alternatively, should subsequent observations revise the mass estimates downward, aligning more closely with conventional expectations, the primary lesson shifts toward understanding how observable phenomena such as coma activity, gas outflows, and thermal physics might mislead observers into inferring exaggerated physical properties. Such a correction would mark a significant advance in our comprehension of non-gravitational forces at play in cometary physics. It would underscore the importance of disentangling the complex physics of momentum transfer, how escaping gases impart recoil forces to the solid nucleus, and highlight the potential for observational biases or modeling assumptions to skew interpretations. If 3I Atlas demonstrates that the relationships between visible activity and inferred acceleration are more intricate than previously believed, then comet physics models across the field will require comprehensive updates. This could involve integrating new insights into the complex pathways through which gases, dust, and metals are released, transported, and detected. For example, the puzzling absence of ion emission lines from nickel, despite prominent neutral nickel lines, poses a significant challenge to standard models of metal release in cometary environments. It suggests the possibility of exotic chemical compounds or unconventional physical processes at work, pushing theorists to explore novel chemical pathways such as unusual sublimation mechanisms, photostimulated desorption, or the presence of atypical mineralogy. These investigations will likely generate extensive theoretical and laboratory research, aiming to reconcile observed spectral peculiarities with a physically consistent model. In essence, the ongoing and future studies of 3I Atlas will serve as a catalyst, prompting refinements in our understanding of cometary physics, the chemistry of volatile compounds, and the processes that govern the survival and transport of large debris across the galaxy. Whether the object's true mass aligns with initial estimates or with more conventional expectations, its peculiarities will stimulate a wide array of scientific inquiries, fostering a deeper comprehension of the physical laws and chemical pathways that shape interstellar matter. This pursuit exemplifies the dynamic interplay between observation and theory, where anomalies serve as vital opportunities for scientific advancement, challenging assumptions and inspiring innovative research directions. Models based on photodissociation, the complex interactions akin to molasses flowing through organometallic structures, and the selective sublimation of metal-laden phases all serve as sophisticated theoretical frameworks, capable of elucidating the peculiar emission patterns observed in interstellar objects like 3 Atlas. To rigorously test these hypotheses, scientists must turn to meticulous laboratory experiments that simulate the extreme conditions of space, particularly low temperatures and pressures, and employ advanced chemical modeling to understand how such materials behave in the frigid, sparse environments found in the outer regions of stellar systems. The intriguing chemical signatures detected by the James Webb Space Telescope, notably the rich presence of carbon dioxide, introduce an additional layer of complexity. These findings suggest that the formation conditions of such objects diverge significantly from those of typical solar system comets, which usually originate in comparatively warmer zones closer to their parent stars. Instead, the data indicate these interstellar travelers may have formed in the coldest reaches of their native systems, where temperatures plummet below -125 degrees Celsius, allowing for the preservation of exotic volatile compounds. Understanding how objects can develop with such unusual volatile compositions necessitates detailed models of chemical evolution, tailored to these frigid outer zones. These models must account for complex processes such as the condensation of volatile ices and the chemical reactions that occur in environments where thermal energy is minimal. In parallel, efforts to decode the physical appearance and behavior of these comets, particularly their persistent sunward glow and the transformation of their anti-tail structures, will rely heavily on morphological modeling. This involves simulating how dust grains are ejected, transported, and arranged under the influence of dust dynamics, as well as how different viewing geometries can influence our perception of their features. These investigations promise to deepen our broader understanding of dust grain physics within cometary environments, offering insights that extend beyond the realm of interstellar visitors to include the many comets within our own solar system that exhibit similar phenomena. One of the central puzzles remains: why does 3 Atlas display such a markedly unusual morphology compared to previous interstellar objects like Borisov or 2I, which behaved in a manner consistent with familiar solar system comets? Unraveling these differences could shed light on the diverse processes that govern formation and evolution in various stellar environments, revealing how conditions in distant regions of the galaxy give rise to a wide spectrum of cometary characteristics. Furthermore, the implications of these observations are profound for our understanding of galactic populations of interstellar objects. Should massive interstellar visitors like 3 Atlas prove to be more common than initially thought, existing theories of debris ejection and transport between stars would require fundamental revision. The upcoming deluge of discoveries anticipated from the Vera C. Rubin Observatory, which is poised to detect dozens or even hundreds of interstellar objects annually, will offer a wealth of statistical data, enabling scientists to refine their models of size distributions, chemical compositions, and orbital parameters based on large sample sizes rather than isolated case studies. In light of these developments, the idea of interstellar objects acting as seeds for planetary formation, the so-called planet seeding hypothesis, will gain renewed momentum. If the massive nature of objects like 3 Atlas turns out to be typical rather than exceptional, it could imply that such visitors play an active role in rapidly initiating planet formation within young stellar systems. To evaluate this possibility, researchers will need to develop more sophisticated models that incorporate capture cross-sections, the likelihood of an object being gravitationally ensnared, along with the survival probabilities of these objects during their integration into planetary disks and their subsequent evolution. Such models will require an intricate coupling of stellar dynamics, how stars and their systems move and interact, disk evolution, how the circumstellar material changes over time, and planetary formation physics, all pushing current computational capabilities to their limits. If these interstellar visitors are indeed frequently captured by nascent planetary systems, they could serve as previously unrecognized catalysts, providing the necessary mass and material for rapid planet assembly. This pathway would challenge traditional theories that rely solely on gradual accretion from local disk material, offering a new perspective on how planets can form swiftly in the early epochs of stellar development. The cultural significance of the discoveries surrounding 3I Atlas stretches far beyond the realm of technical astronomy, delving into profound questions about how scientific communities interpret and respond to anomalies. This celestial object has sparked widespread dialogue about the delicate boundary between credible scientific inquiry and unfounded speculation, an issue that will undoubtedly shape future approaches to evaluating extraordinary data. In an era where social media amplifies both the dissemination and the misinterpretation of scientific findings, the coverage and public fascination with 3I Atlas exemplify both the tremendous opportunities and the considerable challenges of conducting forefront research in this digital age. The widespread attention has underscored the importance of responsible science communication. Researchers and communicators must now carefully weigh not only the accuracy of their messages but also the potential for preliminary results to be misrepresented or sensationalized. As unconfirmed hypotheses and early data rapidly circulate, there is a pressing need for strategies that convey genuine scientific enthusiasm while maintaining appropriate skepticism. Transparent explanations about the provisional nature of initial findings and the rigorous peer review process are essential in preserving public trust and scientific integrity. Historically, responses to such anomalies tend to follow a pattern. Early observations often generate multiple, sometimes conflicting explanations. Over time, as additional data accumulates and theoretical models are refined, these explanations tend to converge toward consensus. This process, which can span years or even decades for truly perplexing phenomena, emphasizes the importance of patience and interdisciplinary collaboration. The case of 3I Atlas highlights that no single framework currently accounts for all its peculiarities. Instead, a multidisciplinary effort involving astronomy, Planetary science, chemistry, and physics is crucial. These fields must work together to develop a coherent understanding of the object's diverse and anomalous characteristics. Laboratory experiments will be instrumental in testing competing hypotheses. For instance, experiments simulating metal emission mechanisms, dust grain behavior, and chemical processes under the extreme low temperature and low pressure conditions of cometary environments can provide critical, definitive evidence. Such empirical data will help validate or refute models, narrowing the range of plausible explanations. Concurrently, advancements in computational modeling are essential to tackling the complex multi-physics problems posed by observations of 3I Atlas. Simulating the interactions of gas dynamics, dust transport, chemical reactions, and radiative transfer requires sophisticated numerical techniques that push the boundaries of current computational capabilities. The influence of the 3I Atlas case extends well beyond its immediate scientific context. Its peculiarities are driving broader progress in understanding comet physics, stellar medium interactions, and planetary formation processes. Even if future investigations ultimately attribute its features to conventional phenomena, the research inspired by this object will accelerate developments across multiple scientific disciplines. Crucially, the value of 3I Atlas lies not only in what it reveals about itself, but also in how it acts as a catalyst for generating testable, falsifiable hypotheses. These hypotheses serve as the foundation for future observations and experiments, fostering a rigorous scientific environment where ideas are continually challenged and refined. Ultimately, the ongoing investigation of 3I Atlas exemplifies the dynamic interplay between observation, theory, and societal perception. Its legacy will be shaped by the extent to which it prompts the scientific community to develop more robust, interdisciplinary frameworks and more effective communication strategies. This case underscores that the true scientific value of such anomalies resides not merely in the data itself, but in their power to inspire innovative thinking, rigorous testing, and a nuanced dialogue about our understanding of the universe. The realm of theoretical interpretation surrounding the enigmatic interstellar object has become both a fertile ground for scientific challenge and a promising avenue for deepening our understanding of how matter behaves and changes across the vast expanse of cosmic time. Whether the insights gleaned from 3I Atlas will ultimately prove groundbreaking, revolutionizing our perception of interstellar phenomena, or will simply reinforce existing paradigms, it has already succeeded in compelling astronomers and researchers to reconsider the fundamental processes that operate between stellar systems. This ongoing intellectual dynamic, often described as a ferment, provides a vital contextual backdrop against which we must evaluate the spectrum of interpretations, ranging from fringe hypotheses to mainstream consensus, that the object has inspired. This discourse takes place within a complex media ecosystem, which vividly illustrates the intricate ways in which scientific uncertainty is translated into public narratives. On one side, some outlets amplify and highlight speculative ideas, ranging from advanced technological explanations to the possibility of artificial origins, often pushing the boundaries of current understanding. On the other side, there are voices that push back equally forcefully, emphasizing caution, the preliminary nature of the data, and the potential for natural explanations that still await comprehensive validation. This polarization underscores a fundamental challenge faced by science communication. In an era where nuanced, carefully qualified insights often get overshadowed by headlines emphasizing sensational or definitive conclusions, an examination of how different media platforms interpret and present the same scientific data reveals a remarkable variability. Certain outlets tend to spotlight the statistical improbabilities and unusual characteristics of 3I Atlas, those features which some interpret as potential evidence of artificiality. while others stress the provisional status of the mass estimates and highlight the plausibility of natural phenomena accounting for the observed anomalies. The most vocal advocate of the technological interpretation has been Harvard astronomer Avi Loeb, whose statements often demonstrate a nuanced understanding that contrasts with simplified headlines. Loeb generally frames the possibility of artificial origins as an open question, an intriguing hypothesis that merits further investigation rather than a conclusion already established. His approach emphasizes the scientific methodology of hypothesis testing, exploring various scenarios, calculating probabilities, and weighing the likelihood of natural versus artificial explanations, especially when conventional physics appears insufficient to fully account for the observations. This approach exemplifies legitimate scientific hypothesis generation, an essential part of scientific progress. However, the line between cautious speculation and definitive conclusion can become blurred in the broader public discourse. Critics of the technological hypothesis argue that extraordinary claims require extraordinary evidence. They point out that despite the unusual features of 3I Atlas, the current observations fall short of providing irrefutable proof of artificial origin. They emphasize that cometary physics, while still not entirely understood, remains a robust framework within which many anomalies could eventually be explained through natural processes. A key point of contention hinges on the orbital geometry, specifically the Chattir-Tochka-Odin degree inclination relative to the ecliptic plane. Proponents of the artificial origin theory interpret this small inclination as statistically improbable under random interstellar arrival scenarios, citing that such an alignment would occur only roughly once in 500 cases. They suggest that this statistical anomaly might be indicative of an artificial or engineered trajectory. Conversely, critics counter that this inclination could be a result of observational biases, a selection effect stemming from survey geometry, meaning that our current detection methods are more likely to find objects traveling along or near the ecliptic plane, which is the plane of the solar system's planets. Therefore, the seemingly improbable alignment might not be as meaningful as it appears, and further analysis is necessary to distinguish genuine anomalies from artifacts of the detection process. The timing of perihelion, the point in an object's orbit where it is closest to the Sun, introduces yet another layer of contention among scientists and observers alike, because the same set of facts can support markedly different interpretations. As the object approaches its perihelion, it does so on the far side of the Sun relative to Earth's vantage point. This positioning results in an extended period during which Earth-based observations become severely limited or entirely impossible, owing to the intense solar glare that obscures the object. This observational blackout can last for months, complicating efforts to monitor and analyze the object's activity during its most crucial phase of solar approach. Some commentators interpret this observational gap as a deliberate attempt at evasion, suggesting that the object might be hiding or maneuvering to avoid detection, while others argue that such an explanation is overly speculative, emphasizing instead that this is simply a natural consequence of orbital geometry. The official stance of NASA, for example, exemplifies a conservative scientific approach. They regard the object as a natural interstellar visitor, adhering to conventional explanations rooted in well-understood physics. This position is rooted in the methodology that the scientific community generally follows, assuming ordinary natural causes unless definitive evidence indicates otherwise. Such caution helps prevent premature conclusions about extraordinary origins, maintaining a standard of rigor that ensures claims are only accepted once solid observational evidence rules out all conventional possibilities. Furthermore, NASA's detailed geometric analysis explicitly addresses and dispels the notion of intentional evasion. They clarify that the object's trajectory follows a hyperbolic path, determined by its initial velocity vector and the laws of gravitational physics, rather than any conscious navigation or control. The fact that perihelion occurs on the Sun's far side, from our perspective, is explained as a product of the inherent geometry of the solar system and the object's orbit, an outcome that arises purely through mathematical coincidence, not design or deception. In high-quality scientific discourse, responsible speculation involves defining clear criteria that could, if observed, decisively shift consensus toward an artificial or engineered origin. Such smoking gun signatures might include sustained powered maneuvers that exceed what outgassing physics can produce, the detection of narrow-band radio signals that suggest communication, reflectance patterns indicative of engineered surfaces, or trajectory deviations that cannot be explained by natural ballistic motion. These objective standards serve as benchmarks for evaluating claims of technological or artificial interference, moving beyond subjective interpretation of ambiguous data. The current absence of such definitive signatures suggests that, despite the intriguing anomalies observed, the evidence remains insufficient to draw extraordinary conclusions about the object's origins. Scientific prudence, therefore, dictates that these phenomena be interpreted cautiously until further data clarifies the situation. Meanwhile, efforts to debunk or contextualize the anomalies remind audiences that the features observed, such as comet tails and volatile spectra, are entirely consistent with what astronomers expect from natural comets, including those originating from interstellar space. For example, the behavior of Oumuamua and Borisov demonstrated that interstellar comets can mimic the activity and spectral signatures typical of solar system bodies, establishing a baseline of normal behavior against which anomalies can be measured. The story of 3 Atlas exemplifies how modern scientific communication unfolds, through an intricate interplay of peer-reviewed publications, conference presentations, preprint repositories, social media platforms, and traditional media coverage. Each channel operates under different standards of evidence and verification. Preprint servers like ARKiv, for instance, enable scientists to rapidly share preliminary findings before they undergo formal peer review. This accelerates the dissemination of time-sensitive data, but also carries the risk of amplifying results that have not yet been thoroughly vetted, leading to the circulation of early mass estimates and hypotheses that may later be revised or rejected. In the case of 3 Atlas, some mass estimates circulated through preprint platforms before publication in peer-reviewed journals, creating both opportunities for scientific discussion and the potential for premature or overconfident conclusions, highlighting the importance of cautious interpretation and rigorous review. Online platforms such as personal blogs and independent media posts serve as alternative arenas for scientific discourse, often operating beyond the boundaries of formal peer review. These venues foster inventive hypothesis development and facilitate direct engagement with the public over the frontiers of cutting-edge research. However, they also open avenues for speculative ideas, sometimes unfounded, to gain undue credibility through rapid viral sharing and widespread dissemination. The collaboration between academic institutions and media outlets plays a vital role in shaping how scientific discoveries are communicated to the public, influencing the level of nuance and accuracy conveyed. The coverage surrounding the discovery of 3I Atlas exemplifies both effective science communication and the risks inherent in premature or sensationalized reporting. On the one hand, it highlights successful efforts to present complex scientific ideas with clarity and context. On the other, it underscores how initial, tentative findings can be oversimplified or exaggerated, especially when amplified by social media. These platforms tend to create feedback loops in which speculative narratives, initially based on preliminary data, are further reinforced, often referencing themselves and inflating their perceived consensus. Such dynamics can give rise to false impressions that a scientific community widely supports hypotheses that are, in fact, still highly uncertain. The virality of extraordinary claims often outpaces the more cautious and methodical processes of scientific validation. Responsible science journalism strives to differentiate clearly between what researchers genuinely state and how those statements are interpreted, sometimes out of context, by others. Thoughtful reporting emphasizes the importance of caveats and uncertainties, while also presenting alternative explanations for puzzling observations. It provides the necessary background on the rigorous methodologies and standards that underpin scientific evaluation, particularly when claims appear extraordinary. Educational opportunities abound in observing how scientific speculation transitions into public understanding across various communication channels. The case of 3I Atlas offers real-time examples of how hypotheses are formulated, scrutinized through peer review, and either supported or challenged by accumulating evidence. The object itself exemplifies how genuine scientific mysteries can attract both serious research inquiry and fringe theories simultaneously. Discerning between legitimate investigation and unfounded conjecture hinges on understanding the operational standards of professional astronomy. The rigorous criteria for evidence, validation, and reproducibility. In this context, enhancing public media literacy is crucial for navigating the complex landscape of scientific information. The line between legitimate scientific uncertainty and speculative ideas can become blurred when preliminary results are presented as definitive facts, or when extraordinary claims compete for attention alongside more mundane, well-supported explanations. Promoting critical thinking about scientific claims, while maintaining an appreciation for genuine discovery, is essential. This approach encourages a balanced perspective that fosters curiosity and open-mindedness without succumbing to unwarranted skepticism or credulity. Even when fringe theories or speculative discussions related to 3I Atlas prove incorrect or are later debunked, they serve an important function. They stimulate dialogue, inspire further investigation, and underscore the importance of maintaining scientific rigor amid popular interest. The process of open debate, critical analysis, and eventual clarification exemplifies the healthy evolution of scientific understanding, demonstrating the value of diverse perspectives in the pursuit of truth. These discoveries serve as a vital bridge between public curiosity and scientific rigor, actively engaging communities with profound questions about the universe. They inspire more meticulous and thoughtful analysis of traditional explanations, fostering a culture of critical inquiry. Moreover, such phenomena offer invaluable educational opportunities, illuminating how science truly functions when faced with observations that defy easy understanding, challenging us to think beyond established paradigms and encouraging a deeper appreciation for the scientific process itself. Looking ahead, the way we communicate about extraordinary astronomical findings will undoubtedly evolve based on lessons gleaned from the media cycle surrounding the discovery of 3I Atlas. Central to this evolution is the importance of transparently labeling initial results as preliminary, emphasizing their tentative nature while still conveying the excitement and potential significance of the findings. It is equally vital to present multiple plausible explanations, whether rooted in natural processes, artificial origins, or entirely exotic phenomena, so that scientific discourse remains open-minded and comprehensive. Maintaining a careful balance between healthy skepticism and genuine enthusiasm ensures that the public remains informed without jumping prematurely to conclusions. This approach, which values diverse perspectives, ultimately strengthens the scientific enterprise, whether advocates favor conventional natural explanations, consider the possibility of artificial or alien origins, or propose more speculative hypotheses. Their engagement enriches the investigative process. Such intellectual diversity, when channeled through rigorous methodologies, promotes creative thinking, an essential ingredient in deciphering phenomena that challenge our understanding and push the boundaries of current science. As we draw this chapter to a close, we reflect on the legacy of the silent giant, 3I Atlas, as it continues its voyage toward the distant edges of the solar system. Despite carrying more questions than answers, this cosmic visitor has already prompted a profound shift in our worldview. It has compelled us to recognize that the universe operates on scales and through mechanisms that still elude our most advanced theories, reminding us that our understanding remains incomplete. Whether the initial mass estimates are confirmed or revised, and whether the observed chemical anomalies are explained by known physics or hint at new revolutionary principles, 3I Atlas has already achieved something extraordinary. It has transformed the study of interstellar objects from a niche curiosity into a structured, systematic scientific discipline. The innovative techniques developed, ranging from precise astrometric campaigns involving hundreds of observatories to rapid response protocols linking space and ground-based assets, have laid a robust foundation for future exploration. Sophisticated chemical models that interpret exotic volatile compositions will serve as invaluable tools for generations of astronomers seeking to unravel the secrets of distant worlds. Moreover, every subsequent interstellar visitor will benefit from the advanced observational and theoretical infrastructure established through the study of 3I Atlas. Perhaps most significantly, this object has demonstrated that the space between stars is not a barren void, but a vibrant, dynamic reservoir of material, an active repository that encodes the history of planetary formation and evolution across the galaxy. Each interstellar traveler acts as a messenger, carrying within it a chemical and physical signature, a relic of environments we can only glimpse through their passing. These visitors open a window into stellar systems that we will never directly visit, bearing clues about conditions that existed billions of years ago in distant solar systems. The hypotheses surrounding planetary seeding, the tantalizing prospect of technological artifacts, the puzzles posed by population statistics, and the chemical mysteries unveiled by 3I Atlas will continue to fuel scientific inquiry long after the object itself has faded from view. In this way, the silent giants of interstellar space serve as catalysts for discovery, reminding us that the universe still holds many secrets, waiting to be uncovered through patience, curiosity, and relentless investigation. The profound questions posed by the discovery of 3I Atlas regarding the mechanisms behind its ejection from its origin system, the processes that have allowed it to survive the long interstellar journey, and the biases inherent in our detection methods, touch upon some of the most fundamental aspects of how matter traverses the vast expanse of our galaxy. These inquiries are not merely academic. They hold the key to unraveling the deeper story of cosmic evolution, revealing how stellar debris migrates through space and influences the formation and development of planetary systems across the universe. In a broader sense, 3I Atlas exemplifies the quintessential uncertainty that fuels the very essence of scientific exploration. It embodies the unpredictable nature of discovery, where new observations continuously challenge prevailing theories, prompting us to refine our understanding of the universe. We now find ourselves in an extraordinary epoch, one in which advanced astronomical instruments and surveys can unexpectedly surprise us, unveiling phenomena that upend conventional wisdom. Preliminary data from such observations have the power to question long-held assumptions, and it is entirely within the realm of possibility that the next groundbreaking discovery will revolutionize the way we comprehend the cosmos. This capacity for surprise and genuine discovery remains one of humanity's most valuable intellectual assets, fueling curiosity and driving progress. The media narratives, Public engagement initiatives and educational opportunities sparked by the revelations of 3I Atlas serve as powerful reminders that scientific curiosity continues to thrive, even amid an age often marked by polarization and certainty. Fundamental human questions, whether we are alone in the universe, how planetary systems originate, or what hidden secrets lie within the space between stars, resonate across disciplines and cultures. These questions transcend the boundaries of astronomy and touch on our deepest aspirations and existential curiosities. As we brace for an era of unprecedented discovery enabled by next-generation surveys, 3I Atlas stands as a testament that individual celestial objects can still ignite our imaginations and propel scientific progress in directions we could scarcely anticipate. Moving beyond the study of individual visitors, the shift toward analyzing large populations statistically should not diminish our appreciation for the unique and often extraordinary characteristics that make certain interstellar objects particularly compelling. The legacy of these discoveries extends far beyond the immediate realm of astronomy. It influences how we evaluate evidence, formulate hypotheses, and build a cumulative knowledge base, processes that are vital to the ongoing evolution of scientific understanding. The case of 3I Atlas offers an insightful example of how communities, scientists, institutions, and society at large respond to truly anomalous observations, with a mix of excitement and cautious skepticism, curiosity and rigorous methodology. This balance between open-minded exploration and disciplined analysis exemplifies the scientific method at its best. Ultimately, whether 3I Atlas turns out to be a colossal natural comet bearing exotic chemistry from distant stellar environments, a statistical anomaly that appeared during our earliest systematic surveys of interstellar space, or an entity even more extraordinary, it has already secured its place in the annals of astronomical history. This discovery has compelled us to scrutinize our assumptions more carefully, refine our observational techniques, and deepen our understanding of the processes operating on galactic scales. Though the object continues its silent journey back into interstellar space, the questions it has raised, and the innovative methods developed to investigate it, will influence the course of astronomy for decades to come. In this way, 3I Atlas signifies both an ending and a beginning, the conclusion of our initial reconnaissance of interstellar visitors, and the dawn of a new era in comprehending our broader cosmic neighborhood. The next interstellar traveler might be even more puzzling, more revealing, and more transformative. And confident in the progress of science, we will be ready.